on the YouTube sync. Also.
Hello.
You're live. Well, we are starting. Hello, everyone. Hello, everyone who's following us on YouTube. Thank you very much for joining us today. I'm here with Joachim from ThirdWeb. I'm just learning how to pronounce French words in France for ECC, so this is my first time. Thank you very much for coming. First things first, and this is the second edition of BUIDLEra Developer Day Conference that we're doing in ECC. We started at Denver, and our main focus for this is to bring our ecosystem together and offer workshops, technical workshops to our developers that can be introduced to new technologies and they can play around and then they can apply these into their projects also. So it's like a follow-up of our BUIDLEra hackathon that you're doing online. But for that, more to come later on. Without further ado, I'm sharing the stage with Joachim from ThirdWeb. Thank you very much for coming, and the stage is yours.
Thank you. Thank you for having me. So I am Joachim. I'm the head of engineering at ThirdWeb. For those who don't know, ThirdWeb is a developer platform that makes building Web3 apps ridiculously easy. And today, I want to particularly talk about building mobile apps, which is historically even harder in Web3, and show you how we make it a little bit simpler and hopefully inspire you to build more mobile apps, because it's time. Web3 needs to go to mobile. We can't have global adoption if we're not on mobile. I am also, you should know, an Android developer by career, 10 plus years in Android, like B2C. I worked at Twitch and at Twitter before, building their Android apps. And so when I came into Web3, it was a bit of a shock for me that we kind of regressed to the web days, where in my mind, we were just in the mobile era already. So one thing that I like to open up with is why even build Web3 apps? And it comes with a kind of new paradigms, new technologies, new concepts you have to learn. Although ThirdWeb makes that fairly easy to approach, but there's a lot of talks about how decentralization is good for the new internet. We need to like stop concentrating power into Google, Amazon, Facebook, basically. And that's a great argument. But as a developer, I think the argument that is the most striking to me is that when you build using blockchains, which to me are just public cloud infrastructure, you cut your development time and cost by an order of magnitude. And let me explain why. If you understand how to leverage the blockchain, how to leverage those public clouds, you get identity, ownership, and payments built into the system that you're using. If you're used to building traditional Web2 systems, you have to implement your authentication system. You have to implement your payment system. You have to deploy and manage your databases for your user data and plug that in all together. But using this public cloud come with these properties that if you use them the right way, basically gives you all of this for free. And it almost eliminates entirely the need for your private servers. We experienced this firsthand when we built a Web3 game to showcase our Unity SDK. It's called Web3 Warriors. Highly encourage you to check it out. We built a full desktop game, high quality. It's a roguelike, action-packed game in 3 weeks. And released it to the world with the ability to like fully focus on just the game and actually building the Web3 part, which is you can earn battle points when you finish the levels, which then you can use to like buy skins, armors, and weapons. That part was actually the easy part to build. The whole 3 weeks was just focused on building the game. The Web3 part was super easy. And that gave us, again, identity, all the ownership and use database for free, and all the currency exchange built into it. And it scales because if you hit the network that's decentralized enough, you get back almost like that load balancer for free. So one thing that is the most important, I think, for mobile in particular, is this identity concept. So I said you get identity for free. What does it mean? Well, in the EVM world, at least, there is this standardized concept of one address represents your profile, your identity. And generally, we think about that as EOAs, or at least that was the past. Chains like zkSync make that a thing of the past, thankfully, and we're finally moving out of this historical concept. And in my opinion, actually, EOA wallets was one of the biggest mistakes from this technology, because it actually put a lot of wrenches in our progress. The reason why is that what EOA are like great for is own your own identity and own your own assets, and you're responsible for everything. The reality is that it's scary to a lot of people. It's the equivalent of putting your money under your bed, basically. And yeah, I don't think it's gonna scale to 1 billion people. I don't think most people will trust themselves having just an EOA and backing it and trusting their own backup and making sure that every transaction they sign manually is safe and it's not gonna like do anything that is unexpected. And so mainly when we talk about mobile, it's especially bad because the solutions on mobile are like few apps, wallet apps that have like pretty tough connection protocols. If anyone has tried to build a mobile dApp with wallet connection, you should know the pain, especially lately if you've been through the Wallet Connect V1 and V2 migration. Anyone here has actually interacted with Wallet Connect? Anyone had a bad experience with Wallet Connect?
Yeah.
The room? Yeah.
Yeah.
So this is the thing, like with this kind of foundation, we can't have mobile apps that are gonna grow to like millions and millions of users if you literally like 1 out of 3 will not be able to connect to your app. It's just not gonna work. And so there are some solutions that are emerging. MPC wallets solve some of that. You get a little bit of UX win there. You can just put in your email and some UA will get generated for you and sharded. The nicest thing, in my opinion, for MPC is actually the fact that there's no transaction confirmations, because especially on mobile, imagine playing your game, you finish a level, it goes out of your mobile game to a MetaMask or favorite wallet app just to confirm, put your fingerprint in and back. That's never gonna work. That UX is just terrible. So at least MPCs allow you to have no transaction confirmation, which is already a huge improvement. So there's a step in the right direction. And everybody talks about account abstraction, and we'll talk about this. Maybe that could get us even closer, and we'll talk about the kind of differences there. So one thing that we've done at ThirdWeb is at least try to make it easy for developers to connect any wallet to their dApps on web, on mobile, on Unity. And we try to have like the widest catalog of wallets. So we have non-custodial wallets, the kind of classic MetaMask, Wallet, Wallet Connect, etc. Smart contract wallets like Safe and our own smart wallet solution, which I'll show. And then the last bit here was, you saw at the beginning, this was the email one is a MPC solution here. And then the last one, this one, just a little addition that we added, which we call here this experience like continuous guest, which really what it does is generate a wallet for you on device. And keep in mind this capability because it's actually the foundation of the demo I want to show you and enables a lot of power if you know how to use it correctly. And when it comes to smart wallets, we also have an option in our catalog of the wallet is zk, which actually makes it usable and integratable into apps. Everybody talks about account abstraction, but the reality is that it's more of a framework, more of a high-level concept rather than something that you can just drop in your app without having to like know every single concept. So we're trying to make that easy, and I'll show you the interface later on, so that you don't have to like know everything about user operations, bundlers, masters under the hood. And with those tools, so you can combine those tools in interesting ways. So we'll talk about non-custodial, the MetaMask, Coinbase wallets. That is okay on the web with browser extensions. That experience is, it's gotten us so far, but on mobile, it's just not going to work. You cannot be switching apps like that, and you cannot confirm every single transaction, even the ones that don't cost you any gas. So MPC wallets help. There's better UX. You just put an email. There's no confirmation, but it introduces that middleman, right? There is still someone that holds some shards of your private key. And that might not matter to some people, but it matters to others. And we want to go in a world where if the company that is handling those MPC wallets just dies, all of the wallets don't die with them. We need to kind of come with a solution there. Local wallets, that's what powers the continuous guests from a wallet SDK, so generating wallets in the device. Again, great UX, right? You don't even see that there's a wallet. You can just generate it as I play a start game, you can generate a wallet for me. But there is the backup issue and the initial funding issue. So you need to either have gasless with it to make it an experience that's okay. And the backup, well, if you lose your device, the locally generated wallet gets lost with it. So you either need to implement some sort of like cloud backup or some sort of system there, which again introduces that kind of middleman there that is off-chain and potentially holding a critical piece of the whole puzzle here. And smart accounts, so the 4337 smart wallets, they have an amazing property, which is the programmability. And but they still need an EOA, at least in the current like 4337 form. zkSync helps on that front, kind of trying to getting rid of EOAs, which I think is where we need to go. But there's still the concept of a key, which is your EOA. It's really a key to access your on-chain account. Yeah. And so because that key is another EOA, it comes with all the same problems, backup, recovery, confirming transactions. It doesn't actually solve the problem here. So I came up with a little idea, and this is kind of the first time I kind of like show it off in public, really. It's this idea of like, what if we could have it all? No middleman, great UX, and leverage the programmability of the smart wallet. So I created this little app. I call it Uni Login. It's a wallet abstraction experiment, I call it, where I combine local wallet and smart wallet to make a login system that looks very familiar with a username password, but doesn't involve any off-chain servers. It only utilizes the chain and IPFS storage to create a completely decentralized user authentication system. And it's fully on chain. It is non-custodial. Nothing is actually even stored on the device. So you can lose your device and reconnect with the same username and password. You'll get the same smart wallet behind it. It is cross-device. And because it's smart wallets, you can just enable paymasters, make it gasless. You can add features to your wallet. And it's recoverable. And it's, again, just a standardized wallet that you can connect to other apps potentially. So I actually have a web demo as well. So if you want to try it out, it's actually live right now. And I'll let you scan this real quick, and then I'll show you on my own screen. So give it 1 minute. You guys good? Okay. So so is this. So let me see. I want to show you the mobile app. So the mobile app, I have it on the simulator here. And then I want to show you the web app side by side. And kind of show you that. So I've created a bunch of usernames here. You should try it out too. Let's try a random one. So we're at the zkSync demo, right? So I'm gonna create a new account, and login or sign up is the same thing. Basically, it all works under the hood. I'm gonna show you how. Just gonna put a dummy password here. So what's gonna happen here? I'm gonna check on chain if there's a username associated with this address. This is gonna check a smart contract, and we'll go through it. It's going to be fast here, but then it's going to generate the local wallet, encrypt it, upload it to IPFS, and then register it on my on-chain account. So here I deployed and registered my username and my encrypted key on-chain. What that gives me is that now with this username password combination, I can reaccess that smart wallet from any device. So here I can go from here, and then the same password. And I should be able to access the same. So now it says the username exists. So all it did, again, there is no server. It hit the chain directly. And by the way, fun fact, this little demo here, both the web and mobile, I coded on the plane coming here. So it just shows you, again, back to the first slide, how much you can get done if you understand how to leverage public clouds and the right combination of wallets. So here, this is my same account. You can see the address up here. And I just made, from here, you can make any app you want. You can make like a loyalty program app, you can make a game, you can make a creator platform. So here I just made a little claiming functionality, which claims an NFT from one of my ThirdWeb contracts. And this is all gasless with no transactions because it's using smart accounts with a paymaster. So here I claim a little SCC devcat, and if I refresh here, and I didn't implement the caching here, so I have to relog in. Actually, it would have refreshed. I should have refreshed here. Now it's gonna, like, again, my account is completely synced across devices, and I don't need any servers. That means my authentication system is built. I literally built this on the plane. It took me like a few hours. My user database that linked my user to what they own, whatever data is also all on chain, and I don't need to implement it. And the transfers of assets, of payments, is also like literally one line of code. This saves me so much time. If I were to build this into a full app, I can just focus on like, I was going to build a fake like airline app that shows you like a membership and like some points that you can. I can build all of that, and all the server part is basically almost done for me. So this is the demo. Try it out on your own phones. You can just do any combination of a username and password. It will attach a smart wallet to you, and then you can claim this little SEC cat, and you can then transfer it to your main wallet address or do whatever you want with it. From here, you can do things like our SDK also allows you to like connect to other dApps with like Wallet Connect or stuff like that. So you can imagine I can just add from the mobile app here, a little scan QR code, and I can connect to OpenSea or Uniswap or anything I want, and actually like unbox this account that I've created to use across the entire Web3 ecosystem. So it goes even beyond just my own user authentication system. I actually just like onboarded you to Web3, and now you have an account in this public cloud infrastructure. Just to show you a little bit, so this is the smart wallet. This is the NFT contract. If you've never seen the ThirdWeb dashboard, highly encourage you to check it out. You can deploy a lot of contracts that we have pre-built and custom contracts to zkSync and 900 other EVM compatible chains. And we have really nice, I think, like contract explorer, we call it, that detects which kind of contract you're dealing with. So here it knows that it's an NFT contract, shows you a lot of information, tries to be as helpful as possible. And it's all completely, like, again, interoperable. You can put in any address and see what the dashboard can extract from your contract there. And then, again, like the way I built the little interaction, once I dealt with the user login, which I'll go in a minute, because my contract implements all these standard interfaces, I can do things like get all the own NFTs for this address, which is exactly what I use in this app. So this little cat here. It just took me one line of code. This is the equivalent of fetch my database for this user, which means I need to authenticate first, and then grab, like, set up my server and my gateway to like access all of it. Again, all of that was for free for me. Once you understand this, it should honestly like light a bulb in your head that as a developer, you now have superpowers because you can get products up and running in a matter of hours. So this is what excites me the most about this tech, and I think it's underrated and not enough people talk about it. So let me show you a bit how I made this authentication system here. And it really isn't revolutionary if you think about it. It's just putting the right pieces in the right place and using it smartly. So when you click that login, once you put your username and password, first thing that happens is I hit a account factory, which is very common in the 1427 setup, and check from that factory if that username matches a already deployed smart wallet. If not, I will generate a local wallet on device, but actually don't even save it. I don't even need to put it on disk. First thing I do is encrypt it with your password and upload it to IPFS. The IPFS hash, I can then attach to your smart account contract that I've deployed for you, and attach the username as well, like do the registration. And now you have a smart wallet that is linked to your username and your encrypted key. And that is the combo. Using local wallets encrypted to IPFS attached to your contract makes it so that I basically leverage the programmability of the contract to be, well, you don't even need a server. Your smart contract can store data, it can have programmability, it can have logic. Why don't we use that as the store? And that makes it completely decentralized and cross-device. I don't even need to think about backup anymore, because literally the smart account holds its own key. It's just encrypted with a password. And when you relog in on another device, I can check the account factory again, see that you have pre-deployed an account, get your wallet back, the encrypted wallet, decrypt it with your password, and now you're back up and running your Connect. This little simple combo enables a kind of pretty unique UX, I think, that I haven't seen before, used at least in the the 437 community. And full disclaimer here, this is just a demo. I wouldn't use it in full production. There are downsides to this. Obviously, the password that you have is kind of like now the key, but at least you can remember it. And you need to make it it's as secure as your password is, basically. So if you make a really simple password like I just did, people can brute force the thing and eventually get to it. But again, it's all about like using the right tool for the right job. If I'm building a game or a little social app or something, maybe I don't need maybe the UX straight up is worth it. So again, we're using full production, but I think it deserves the experimentation. And literally, I built this on the plane. So, put another week and I think we can come up with a better system here that actually ticks all the boxes. So what did I do? The first thing I did is the smart contract. So the account factory and the account is the main thing that powers the on-chain logic. And I didn't start from scratch here. That's one of the things that we try to do at ThirdWeb, is like accelerate your development, including on the contract side. We have a lot of these base contracts that you can start from. And so I started from this base account factory and just added my little sauce, which is this registration step, so that I can fetch back, when you try to relog in, a mapping from your username to a ready deployed address. And if you scan this QR code here, you'll go to the published contracts link, which lets you deploy your own one of these, and you can play around with it. But also see the source code and all the ideas and functions. So again, this took like about, 20 minutes once I had the idea. And the credential account is also like one added function from the base one. And then the local and smart wallet is, I think, the interesting combo here. Local wallet, honestly, it's such an amazing tool. You can generate wallets for users. Like, it's useful for so many contexts, in CLI, in mobile apps, in servers too. Like, we use it in a bunch of different places where you just need to generate a quick wallet. And it comes with an API to persist to any location, memory, disk, cloud backup. You can do whatever you want there. It's a very kind of like Swiss knifey tool, and you can reload it from the same configuration. And it allows you to export, import into different formats. It supports private key, mnemonic, and encrypted JSON, which is the standard like JSON wallet format. And that's what I use in my demo. So again, just with a password, it has default encryption in there. You can pass your own encryption. This is kind of a low-level tool. And it comes with another thing that I don't show here, which is configurable signing. So by default, there's no sign step to sign a transaction, which, again, depending on the tool, might be the right thing or might not be. But you can configure that. You can decide your own logic for when to prompt for a signing. So you can make an app that, for most low, like free transactions, don't require any confirmation, but everything that is, say, an approval or anything that has a certain threshold of value require confirmation. And now you can start crafting like actually decent UXs that make sense on mobile and other platforms. So this is a very powerful tool. I highly encourage you to play with it. And then the Smart Wallet API is basically compounding on that, because once again, the Smart Wallet requires a signer. It requires the key. That key can be any wallet. So you can choose any wallet from the catalog of the wallets that we have. It can be a MetaMask, it can be Wallet Connect, it can be Coinbase, it can be an MPC, or it can be a local wallet too. So this is what I show here. I just kind of spin up a local wallet and then connect to the smart wallet with that personal wallet. And that gives me a stable address that will always be the same for that same key. And gasless true or false, and you get all the gasless transactions. We're trying to simplify as much as possible. So again, you don't have to think about user operations. You have to think about bundler paymasters. All you know is that you want this programmable wallet, and you want to turn on and off gasless. That's kind of like the minimal thing you need to do. And then there's a couple other required things there to enable the infrastructure for you. But if you know what you're doing and you want to patch your own paymaster logic, your own bundler endpoints, you can also pass that in the configuration. It's very configurable. Also encourage you to check it out. And so with that, I think hopefully it is inspiring to you that if I was able to put this together in the plane, imagine what you can do with a little bit of knowledge and a little bit of motivation, with authentication almost free. If you know what you want to build and you know the tools available to you, you can craft pretty much any experience you want, from fully invisible to fully have to confirm everything. Reading user data is pretty much free. You have basically a public database that you can hit, and not only you can hit, but others can hit too, which is amazing to think about, because, for example, for the game that we built, well, anyone could come in and build a marketplace on top of it, for example, which is kind of like unseen before. Writing user data, so like writing to this public database, can be sponsored, like I did this, so like I took on the paymaster cost, or depending on your logic, you can share the cost with your users. That also like kind of brings more interesting economic models versus the Web 2, where you have like a fixed server cost, and then you have to figure out your own monetization on the other side. And then this public cloud keeps emitting events that you can hook into. You can build watching systems, you can build monitoring, you can build other UIs that react to things that happen in your apps like this. And again, the magic is that transfer of value payment is literally one line of code. I don't think we can beat that with traditional Web 2 tech. So particularly on mobile, this is something that I'm passionate about. I think it is time to actually bring these innovations to mobile. I think the tooling and infra is getting there. We still have a little bit to do, but once you realize that you can like free yourself from the good old MetaMask and Coinbase wallets and Wallet Connects of the world, you can actually build something very interesting. And we're seeing a lot of influx at the web from gaming companies, e-commerce, social, and creative platforms that are all interested in building on mobile. There's also something that came last week, which is very encouraging, which is that Google announced their blockchain policy for the Play Store. So they have actually now explicit rules, and it does allow for crypto apps with NFT transfers in them, which is a big step forward, and I anticipate Apple to follow suit very soon. And then, thinking even forward, I used to participate in this project called ETHOS, which tries to actually bring all of this UX problems and signing down to the OS level, which I think is the natural next step, but that will take a kind of giant mountain to overcome, which is the the existing established platforms today. But something to watch out for. And that's it. So hopefully you like the demo. Please claim some of those XCC dev cats. They're very cute. They were generated with AI. I didn't draw them myself. But yeah, I hope you enjoyed it. I hope you got inspired. Thank you.
Do you have any
Follow me.
questions?
Yeah.
Yeah. Can you take this? Let me just do another check. 1, 2, 3. Go ahead.
So one question, when I create my wallet through that interface, actually there will be two wallets generated, right? One is an EOA encrypted with my password, and one is a smart contract wallet on the chain. So why not just use the EOA directly?
Yeah, this is a great question. And so let's see, what's the best illustration here? So here, you can definitely use just the EOA, say the local wallet, and reproduce the same experience from the app I did. But you lose two things. One is the gasless aspect. So you could work around it and do like meta transactions, but it does require a little piece of infrastructure in the middle. You can't just go straight to blockchain now. Someone else has to submit the transaction for you. And two, you lose the backup. The problem with just using EOA, and again, like if I use the local wallet in particular, is that if I lose my phone, I can't log back in because that wallet is kind of locked into my device and siloed there. What I use Smart Wallet for here, the programmability that I use here is the fact that contracts can hold data. EOS cannot hold arbitrary data. The Smart Wallet can. I use the Smart Wallet or the account contract as my server backup. It's like my cloud backup, right? And so combining those two, I get not only the gasless, which makes it super easy with Smart Wallet, right? I just put gasless true, goes through a paymaster, everything's handled for me. And two, I can now actually be cross-device because my local wallet is never saved on device. I use the smart account to retrieve the local. Now, there is another combination which is really good as well, which could have achieved this, which is like an MPC plus smart wallets, or just an MPC with meta transactions could have achieved this. But again, MPC, as I said, brings another little man in the middle there, and the meta transaction is yet another man in the middle there. So I was trying to get to this like purest form of client to blockchain with no middleman, and that was the best combo I think I could find.
I get the part of gasless, but
Yeah.
for that wallet,
Yeah.
when you retrieve that from IPFS,
Yeah.
you also need to decrypt it,
Yeah.
and store it like locally, right?
I don't need to store it locally.
But how can you use that? Sorry. So then how can you use that to cite transactions?
So it is in memory. So it is downloaded and saved in memory for signing transactions. But actually in my demo, I never needed to save it on disk.
Okay. So it's not persistently saved. It's always in the memory.
Yeah. In this demo it is. Now you could perfectly also like save it to this to accelerate things a little bit. But the important thing is that I want it to be cross-device, right? So I didn't want to rely on this and always have kind of the on-chain as my cloud backup. Yeah.
But in your demo, so you have you log in on your Mac, and also you log in in your iOS simulator.
Yeah.
So these are two devices, right?
Right.
When you retrieve the wallet from the cloud from IPFS. They are the same wallet.
Correct.
Then how come in my case, the case that I said why not use the UA directly, you don't lose the ability to cross device.
I see what you're saying. You're saying just use a contract as the backup mechanism.
That's
Instead of
what
an
I
account.
mean, yes.
That's totally viable, and that works. But now you have a single contract that has all the wallets instead of each contract on its own wallet. So it's a bit of a design choice. And then the other thing is by using the smart wallet as the holder of assets, you can add the extra programmability on top that you couldn't with just like some sort of registry contract. Some examples could be, I want to not only be able to sign in with username and password, but also add my MetaMask as an extra signer so that I can also access my assets that way. Or I want to be able to, well, the other thing is also the paymaster aspect of it works that way. Like you have to have the kind of 4337 compatible interface there. That also wouldn't work with the registry. So again, you could potentially get away with meta transactions, but the compatibility of target contracts you can hit there is limited, right? The contract needs to allow meta transactions, whereas with Paymaster, you can do everything. You can deploy contracts, you can hit contracts that are not meta transaction friendly. So it is just like a slightly better design, but I think you're right. You could achieve the same thing with a registry and just retrieving basically encrypted wallets in a centralized on-chain registry.
Yeah, that's it. Thank you.
Do we have any other questions? Because the mic was working only for live streaming.
And when you say that you don't need any servers, but you do need some, which servers are we talking about?
So in this demo, there are absolutely no servers. The only like non-local things that happen is, so hitting an RPC to hit a node, you need to hit the chain at some point, and IPFS for the kind of like maybe like cold storage almost. So that's the two things that I use here. I think though, like as a client-side developer, I love building like front ends. I love the idea that I can just build front ends that have no server at all, and just use the chain for everything. The reality though is that I think real like million plus users apps will probably require some indexing at a minimum. We'll probably want to enrich user data with other off-chain sources. So realistically, you're probably going to have a mix of private and public clouds. I think that's where like most of the architecture we see go. But I'm a purist. I'm a believer that we can do it if we get to a world where on-chain data is like really performant to access and really cheap to write to, and scales really well. I think we're getting very close to being able to eliminate all private servers.
Or having decentralized indexers, and maybe I'll choose for
Absolutely.
many of the things.
So that is the kind of the best compromise, is having this non-pure chain nodes to also be decentralized and have the same idea that there is no one single point of failure, but instead like a shared network. That'll be the ideal world.
Yeah.
Thank you for your question. Do we have any other from the audience?
Everybody claim their SCC death cap. What are we up to?
Where we have a question from the live stream.
Okay.
What is missing, zkSync question, what is missing from mobile app development that excites you the most? And mobile app development for Web3?
Yeah, that's a great question. So For mobile, I think the key is getting that wallet's connection piece right. Once you get that piece right, actually the rest kind of flows pretty smoothly. So we have a pretty comprehensive React Native SDK that lets you interact with any contract with very few lines of code. Like the getting the own NFTs I showed you was one line of code. Doing a claim transaction here to claim this guy was also one line of code. So that part is actually pretty smooth. The problem with mobile always was, how do I sign and confirm a transaction? Do I have to like get out of my app and sign and come back? Does it rely on some shaky WebSocket protocol that drops 103 times? And once that gets out of the way and you actually control when to sign and the underlying like private key to actually sign those transactions, then everything becomes like way smoother. And the experience I showed here, and you guys should try it out on the web, but on mobile, it's the same experience, is that it just works. So that was the biggest thing for me that has been the what stops innovate like the progress on mobile was the wallet concept. Like we boxed ourselves into the wrong direction, I think, with wallet apps that need this cross-app communication. And because the system doesn't allow like clean app-to-app communication, we had to come up with this kind of workaround, and it shows the cracks like very quickly. But if you're a mobile app and you know what you're doing, you can actually eliminate this problem entirely and onboard millions and millions of users to Web3 without them even knowing it. You can educate them after the fact. Once they're engaged, let's say you build a social app. Again, like building a social app now becomes like really easy with this because again, the identity and user database is all accessible there. And you can, if you use the chain and full storage smartly, you can reduce the cost significantly so that it becomes on par with hosting your own server and paying AWS. And if you make it look invisible and people are just using a normal social app, at some point you can educate them like, hey, by the way, this account that you've created here is actually interoperable with all these other apps. You can go and connect this other app with your My Social app account and interact there and see the same assets. And that should like give a light bulb to all the users of like, oh, there's actually a separation between the app I'm using and actually the amount of public data I can access with the same identity. I think once people realize that, they'll see that there's kind of a public digital space out there that anyone can access, and that is super powerful. Especially for social apps, especially, I'm very excited to see this. We've seen this with some messaging like apps and then social apps where you can have multiple front ends that show you different, like they kind of like present the same data differently, but give you different experiences. Like Lens is a great example. You have a Twitter-like feed and a YouTube feed, an Instagram-like feed, and an events app, and it all kind of goes back to the same public data and with the same identity. Like if we can get to this world, oh man, it's gonna be so nice. Imagine not having like 7 Twitter clones installed in your apps and 6 messaging apps that all have different like list of messages, and you have to ask your friends, are you on Telegram or on WhatsApp or on like? We should be able to choose any one of those, and the same messages appear. Any one of those social apps, and the same followers, the same graph, and that's what excites me so much. And again, it requires a separation from the apps to the data. The data needs to live in a public cloud that all these apps can access. And once we figure out this wallet problem, I think it just unlocks everything, and mobile devs will be pleased, at least as well as my experience, that you can just focus on building your client, make a really good UX, and all the server-side code is like 80% done for you already.
Well, thank you very much. Do we have any other questions? If not, we don't have questions from the live stream. So thank you very much, Joachim, for coming and presenting for us today.
Okay.
And yes, stay here if we do have questions later on the stream. If not, we all know where to reach you. You shared earlier all of your data. And for everyone who's listening and who's with us over there, we'll get ready for the next workshop. So be patient with us for like 5 minutes until we bring the other speaker on board. Thank you so much for coming.
Thank you.
Test. Okay. Move to the page. And we are back. Thank you everyone for being patient for us and all of the technical difficulties. We have Javier today with us again, and thank you so much for coming in person. We did another workshop for BUIDLEra Hackathon, and that was amazing. And thank you for being that flexible. We appreciate it. Well, without further ado, the stage is yours. From Gelato, Javier, coming the director of DeFi. Thank you.
Thank you very much, Albiona. Hi, everyone. Thanks for having me here. Today, we're going to go through what is Gelato and how can we help bringing off-chain data to smart contracts to elevate your DeFi protocols, your trades, everything that you need to do with off-chain data. Then, first of all, bonjour Paris. I'm Javier Donoso. Last week, I had a white beard. I decided to shave it because it was too hot in Spain, almost 40 degrees. That's why some people didn't recognize me in this event, but I'm Javier Alonso. Then let's start. Actually, the agenda for today is going to be a brief overview about what is the backend architectures of Web3 apps today, how we can build decentralized and serverless Web3 apps using Gelato Web3 functions, and we will have a demo where we will create a stop loss and bounce entry strategy. It's prepared that we can deploy and create the Web3 function live, but with the problems that we have with the Wi-Fi, probably I will use the ones that we have already deployed so we can see how the code works. But if we cannot deploy, then we will use the already deployed. Then let's start. How, when you start in the Web3 space, as I did, like participating in hackathons and creating dApps, first you think that you're going to build a nice front end in React or in Angular or Vue.js, and then you're going to interact with 2 or 3 smart contracts, and that's going to be it. And then you think, okay, with learning some solidity, it's fine. But when you want to introduce some new features to your app, then at the end of the day, your ecosystem looks like this. You need not only interact with the smart contracts, but you also need IPFS to store maybe some metadata for NFTs. You need some blockchain indexes to access previous transaction data. You need somewhere to store your private key vault. You need a job scheduler for automatic executions in a later point of time. You need notification. You need some off-chain data to elevate your application, and you need some reliant for careless transaction in the case that you want to offer this service to your users. And on top of that, you need access to normal Web2 APIs for bringing some intelligence into your smart contract. Then, what happens? Of course, you as a developer, you can build all of these different services. However, you have to scale and maintain all of these services. If you want to have availability of 100%, you will need to interact with different RPC providers, and you will need to pay different providers. And imagine that you need to deploy on different blockchains, and you have also to maintain all of this infrastructure around the blockchain. You will need to have a way to store your private key in the cloud. And at the end of the day, you as a developer, and this is the most important part, you are the central point of failure. Because if something of all of these services is not working, you are responsible for this. And you cannot concentrate in building the features for your applications. Therefore, we in Gelato, we want that you concentrate in building the features for your app, and that you outsource on us the different services and infrastructure. Then, what is Gelato? Gelato, we say that we are the decentralized backend, and we want to empower builders to augment their smart contracts to create reliable, user-friendly, and scalable Web3 apps without sacrificing decentralizing and censorship resistance. What are Gelato Web3 functions? Well, before going deep in the Gelato Web3 functions, we have other 2 services. The first service we have is Gelato Automate, which is like the prompt jobs happening on-chain, and that check all of the conditions within the smart contract. So what happens on-chain? The classic limit order use case, where you say, when the price of the Ether, which is stored in a contract, goes to a certain threshold, please buy or sell Ether. This is the classic automate, use case. Then we also have Gelato Relay, with relay transactions, offering the protocols and applications the ability to offer gasless transactions for the user. We know that onboarding is one of the main problems of the Web3, and offering relaying is a way to decrease the barriers for entry from Web2 to Web3. Then what are Web3 functions? We can see the Web3 functions like AWS Lambda or Firebase Cloud Function or Google Cloud Functions, but for the Web3. And what allow you to do? They allow you to connect to smart contracts, from smart contracts to off-chain data. They ensure that the data is accurate. They can run off-chain computation, which is cheaper than running inside chain. We can execute transactions in all major EVM chains where we are deployed. We can send notifications, and we can index and store data. These are the services that I mentioned before: the Web3 functions, Gelato Automate, and the relaying for gasless transactions. Then how does the Web3 functions work? First, the developer writes some TypeScript or JavaScript. This code will be stored on IPFS. In this code, you can import any NPM models that you are used to use. Then the Gelato node will pick up this code from IPFS and will run this code. We'll do the HTTP calls or RPC calls needed. And then it will, in the case that your logic decides that a transaction has to be published only on chain, then it will pass the transaction to the Gelato protocol, and it will be published on chain. It doesn't have to publish, it doesn't have to execute a transaction by every run. You decide when the conditions are met to execute the transaction. One of the use cases that we have is that we have like fallback oracles that very rarely they execute. They check the price, that the oracle price are synced on chain and off chain. And in the case that are out of sync, then they push prices, but most of the time they are not transacting. Then what are the features of the Web3 functions? We have TypeScript support. It runs in a demo sandbox with any access to the local APIs. It means that it's a very secure environment. We have RPC provider abstraction. It means in the context of the execution, we provide a provider for any chain where we are deployed. It means that although you are executing transactions in a specific network, you can query with RPC flows to any chain where we are deployed. We have some environment variables like secrets, where you can store some API keys that you don't want to be public. These Web3 functions can be public or private. We have in function state management, which is an object of k-pair values. The way of paying is a flexible pay-per usage. Normally, if you are developing, if you only have one Web3 function that runs every minute, it's going to be free. If you are in the free tier, if you want to scale and to have different functions that runs more than 1 minute, then you will have to have a paid plan. It's very high scalability, and we can even spawn Web3 functions from on-chain transactions. We have different use cases that we have seen so far, from dynamic NFTs, from DEX aggregators, bridge aggregators, some bringing results of some games on chain, also how to post ChatGPT messages on the Lens protocol, and different multi-chain NFT limit workers. How we actually, if you, we are talking about executing transaction at a certain point that will be executed by the Gelato node. Then how we pay these transactions, because it's clear that no one is launching these transactions. We have the so-called one balance, that is a system that allows you to deposit USDC on Polygon, and you will pay for every transaction in every chain that you want to interact. It means that you don't need to have native tokens for Avalanche, Arbitrum, Polygon, or Ethereum. Only depositing USDC on Polygon, and all of the transactions will be paid with the one balance, and every transaction will be subtracted from your balance. That helps a lot, actually, the management when you have deployed and you want to use Web3 functions in different blockchains. Then, actually, for the hackathon, we had $4,000 bounty. The first one, split it in 1,500 US dollars in gel for the best implementation of a Web3 function, and 2.5 thousand US dollar in jail for a prize pool for all of the projects that qualify with a Web3 implementation, either from Relay or from the Web3 function. Our ecosystem is actually quite big. We have integrations with more than 400. I think even now it's 500 different partners. Almost every big player in the space has already integrated us, and we are present in all of the chains that you see there. Almost any important EVM compatible chain. And actually, we are now trying to shorten the period of deploying to new blockchains, so we can keep up with all of the new networks that are coming. Then let's go to the demo. What we are going to demo. We are going to build a very easy strategy. We have a contract, which is the mock swap contract, where we can swap USDC with Ethereum. We are not going to have USDC or Ethereum wrapper ETH in the contract. It's only to be a number, but what is important is to understand the mechanism. Then first of all, we need what is very important is we need to set an operator, like the delegator, that will act on your behalf, because the one who is going to execute your trades is going to be the Gelato proxy contract. The Gelato proxy contract is dedicated message sender associated to your address, the address that creates the task. It means that you are in control of this proxy contract, that is the one who is going to execute the transactions on your behalf on your contract. Then first, we need to set the operator. And second, we will deposit some amount. In this case, it's only a number. And we will require that either the message sender is the user or the operator that we set before from the user. And then we will add the USDC balance in a mapping, which is not really fancy, but we will keep track of the balance. Then when we are going to do the swap, and actually the swap is going to be executed by the dedicated message sender, the proxy contract, which is associated to your user. Then in the case that we have to buy, it will swap the numbers. And we will pass the user, the price, or whether we have to buy or sell. Here is how we interact locally with the contract. To set up the scene, first we're going to deposit some fake ETH, some fake USDC, sorry, and then we're going to set the operator to the dedicated message sender of this user. We're going to see in the Web3 function later that this is the proxy contract associated to the user. Then this is a part of the Web3 function that later we will go in detail, and this is how we return the transaction data to be executed on-chain. First, we have the price. This price, we will see later, but we get it from a Uniswap NPM module. Actually, we interact with Uniswap to get the current price between USDC and wrapper ETH. Then we use a classical encode function data. The method is swap, and then we have the call data for the transaction that we want to execute. And simply, the Web3 function returns canexec equals true, and this is the call data to the mock swap contract address and the call data that we just created. As you can see, this is an array of call data. It means that if you have to execute different transactions with the same run, you can do that. You can pass here a list of transactions to different receivers and call data, and it will be executed. Then, okay, then let's have a look at the code. First, here we have the Twitter zkSync repo, and we have adapted, including the Hackhat plugin with the Web3 functions, so we can test locally all of the different functionality, and we have added the Web3 functions folder. Here we have our trade, And let's have a look how it looks like. This is actually the context where this is the piece of code that is going to run from our node operators. And we pass the context where we can take some user arguments that we define at the beginning. We can pass the storage, what we want to be stored, the secrets, if we have some specific environment keys that we have to keep secret, and the multi-chain provider. In this case, first I initialize the provider for zkSync, because this is the negotiation where we are in, and I also initialize the provider for Polygon, because I will need this provider for the Uniswap price pool. Then first I get the user and the contract from the arguments that I will pass at the beginning of the definition of the task. Second, I will store and I will get the last min and the last max of the price. And I will do this because in this strategy, what I'm gonna do is, if I'm not in a trade, if I still have my USDC, if the price is going up, if the price then goes up more than 2%, then I will enter the trade. And then the trading stop, it will go up at the same time as the price goes up. In the case that the price goes down, then I will exit the trade. Then I have to keep track. I have to keep a record of the last min and the last max, because the same way, if the price is going down, I'm not going to enter the trade, but when it suddenly goes more than a certain threshold from the last min, then I will enter the trade. That's why we call it bound entry. And in every run, we have to keep track of the last min and the last max of the price. So we can go up with the trading stop, and we can go down for the bound entry. The entry and the exit are the thresholds that I want to establish, like 2% for exiting the trade or entering the trade. Then I instantiate the mock swap contract. First, I get the user balance from the mapping we just saw before. Then I get the Uniswap price using the Uniswap package. Then here we will see before, if we are not in a trade, that is the beginning of the execution, then first I should buy the Ethereum, the wrapper ETH. Then we go to the return call data, and this is the piece of code that we saw before. Then this function is already executing. Here you have our Web3 function. This is the hash of the IPFS code that we deployed before. We're going to do it live later, but I don't know if it's going to work with the Wi-Fi. This is the user. This is the contract that we're interacting with, that we have actually here. This is in zkSync mainnet. This is the so-called dedicated message sender, this proxy contract I mentioned before that is associated to your user and allows you actually to execute all of the transactions on your behalf. It means that you only have to, in this case, set the operator to this dedicated message sender to ensure that only your proxy contract can execute this transaction. Then, if you see, we had here a first execution, and then in the next days, it was no significant change of prices. That's why it did not change, it did not execute a sell, because now we are in a trade. And if we see the logs, this is the executions that are happening every minute. And we can see that it says no trade exit because the price has not changed. And every minute is logging what is happening with the price. Then every minute, our node executors goes to our code, execute the code, and in the case that there is no significant price changes, log that is not going to execute anything, and wait until the next one. And update the price, either high or down in the case that we are in a trade or not. This is the code of the Web3 functions that is from IPFS. This is the storage where we store our last and max and last min. And I could have used the user arguments to define the entry and exit, but to showcase how the secrets functionality works, I put them here. Then it means that in my case, I say if there is 2% for enter the trade, and if it's 2%, then exit. Then let's have a look on the code. And what time is it? Okay, we are still. We have 6.
Can we ask a
Yes,
question?
sure.
When you go back to the code, it said we're previewing unverified code. How do you verify? Have you verified?
Yeah, actually, it's always unverified. What I want to highlight here is that this is the code of the user that actually put this code on the on IPFS. It's not our code, and we haven't looked whether it does what it should do. That is the responsibility of the developer doing the user. We wanted to highlight here that it's not Gelato code. So first, what we have to do is to deploy our Web3 function to IPFS. As you can see here, we're going to run this npx w3f, which is part of our hardhat plugin. Actually, if we go to our hardhat config, we can see that here we have the specifics of zkSync for the hardhat config. And then we also have our Web3 functions hardhat plugin, where we pass the networks where we're going to interact with. And in the case that we want to try it locally, we will have to put in our environment variable the RPCs that we want to try. In production, we provide all of these RPCs for you, but locally you have to provide it here. And this is how you do it. Then, before deploying the Web3 function, something which is very interesting for developers is always that we can try all on hardhat, and that actually we can impersonate the different actors, and we can see whether the results are expected, because unit testing sometimes is difficult. And in this case, if we go to the zkSync documentation, you will see how to create some local testing. I thought it was here. Let's see. Well, I don't find now the page, but if you Google zkSync local testing in the docs, I found that like 500 times this last week. Then what you have to do is you have to download and clone a repo with the name is local setup, and then you instantiate 3 instances, 3 images of the Docker container. This is the Docker container. You have the Ether, the Postgres, and the zkSync image, and then it's working here. You have to take some time. That's why I started before, because it takes like 5 or 6 minutes to run. But then you can actually test locally your code. If we do yarn test, then let's have a look. First, we're gonna see that it works. If already we are here, it means that it's connecting properly with the local environment, and it's actually executing, it's deploying the control and executing the Web3 function against the control. And if we have a look on the test contract on the test, what is interesting to see is that first, well, all of this is like classical hardhat deployment. But what is interesting is that here we are mocking the execution of the Web3 function that happened in the Gelato node. Then we get the result, and you remember that we are always returning can exec equal true or can exec equal false. Then we say if can exec equal to true, then take the call data that we return and send the transaction from the deployer to the target contract. And then we can we wait for the transaction, and we check that actually it happened properly. And then we can mock the storage, passing these arguments for the next run of the Web3 function. It means that locally we have the ability to test something that is happening in the Gelato nodes. And actually, believe me, because I'm doing this kind of proof of concept and integrations with users, this is amazing. The first time that we have the hardhat plugin, your development speed increased by 5 times because you don't have to deploy the Web3 functions, execute the Web3 functions, and check. Here, actually, you can do that all locally. Then once we have our results of the local test successful, we're going first to deploy. But no, we're gonna go for the big prize. We're gonna deploy the contract. I think internet now is working better. We are running the script for deploying the contract. We are verifying the contract with the zkSync plugin. Great. We have this contract. Let's have a look. So far, so good. Contract is verified. It looks promising. Now we're going to deploy our Web3 function. It's going to upload to IPFS, and it's going to return our CID, and it also returns the URL for creating the task. You can also go to the application yourself and create the task, but that helps you with one intermediate step. Then let's go here. It says the URL. Good. Here is our CID. Then we have to pass the contract that we just created, and we're going to pass the user, and the user was this. That is the home address, not the one that we deployed. This is our user, and this is our user. And this is zkSync. We want to add some secrets. The entry. We're going to put 1%. We're going to put the exit, 1%. And that's it. We're going to call it Paris zkSync. Today is the entry. Then let's create the task. You can see here, no, not yet, it's actually when it's deployed. Then let's wait, sign in, confirm the transaction, and now we're gonna wait some seconds until the transaction is executed.
What do you have to sign?
We have to sign, you mean the difference between why we sign?
What are you signing right now?
You are signing the secrets, actually. That you are the one providing the secrets, because one thing is the transaction to execute to create the task, and the other is where you sign that the secret is going to be stored. The secrets are stored centralized. It's not on our not executors. You are signing that you are the one putting the secret. In the meantime, have you see the confetti? Yeah. Then now let's wait for the logs. It will take some minutes. And probably the first run, it should do execution, because as we have the fake USDC, it will buy the Ether with the current price. Then let's wait some seconds, but it should then execute the transaction. And in between, we can, if you have some questions, because more or less that is the end of the presentation.
There was a proxy there. There was like a proxy user.
Exactly.
How
This one is a proxy.
was it created?
This is created when the first time you create one task, it will be created. The second, third, and fourth task that you're going to create is going to already to be there for you. It's a proxy contract that acts as a forwarder. It has execute and execute by just methods.
And who owns the private key store?
And you actually the same user as the address creating the task. Actually, I'm here logged in with this user. This one is the owner of the proxy contract. And actually it doesn't have any, only you, this user, can interact with the proxy contract.
Actually, your server does. Right?
The server,
So the server also had a copy of this private key.
the server has a copy, no. No. Actually, it has the proxy contract can be executed from the dedicated message sender and from our nodes, but it doesn't have the keys. Sure. Let's have a look if no price change. Actually, it should have done the first execution. Well, something I didn't quite, probably I didn't copy properly, but it works before. Then some questions. Actually, what is very interesting is that we are seeing very different use cases that come and ask us how to use virtual functions. One use case is one ball that is actually streaming with Superfluid at certain percentage for paying the fees, and every day it checks the amount that is in the ball, and every day, every 24 hours, it updates the flow rate to pay to the protocol with the virtual function, with a virtual function. We are also seeing different low latency oracles like Thieves or Redstone that are in zkSync too. They are using us to customize different types of oracles for different users. API3, we're going to work with them too. Actually, we are having different use cases, actually very interesting. We have some customers that is trying to create like some recipes of trades with a Web3 function with this IPFS, and then allow from the front end to create the task dynamically, add the user arguments, and create a specific trade with a recipe for this user. And all of this is possible.
Do we have any questions? If not, we are checking the live stream to receive any questions in the next few minutes. And
What about the security model? How much do I have to trust you?
Yes, you have to trust that our executors are actually going to execute legit code. And for the time being, we are in a way of decentralizing. In the last months, we have some nodes that started to stake into the network, but they are still under contract. It means that you cannot be a node without having a contract and passing some due diligence with us. In the future, anyone could be an actor of the system, but staking a certain amount that could put you that you will lose in the case that you don't have legit action.
To decentralize, at the end of the day, a single node is doing the call to the zkSync, right?
Well, it will be a kind of consensus. It will be an algorithm that how it's working. I'm not really expert on how the infrastructure will work later, but we have done the first step, which is accepting external nodes to stake and to participate into the network. We are having already the first rewards of the execution, but how the process is going to be in detail, I don't know. I can put you in contact with our infra team. They are really good on this.
This is actually the interesting case. You know, how do you keep secrets secret? How do you make sure that storage doesn't get like modified by malicious hackers? Because just looking at this quickly, it's like, hey, I'm kind of handing you over the keys and saying like, please don't lose them, or like, don't drug pull me, right?
Correct. Yeah, at the end of the day, as we can execute through the proxy contract, and your proxy contract is true that you have to trust that the Gelato nodes are executing legit code. Well, I don't know why not. It should have executed.
And how do you debug that?
Well, in this case, probably it's because I did the one test passing some price before, and probably the price is not matching. That's why it didn't get to the percentage. Because when you are, but actually debugging, the best way is to do it with the unit testing, because you can do exactly what we saw in the unit testing. It was executing the transaction. That's why we could have the can exit equal true. And for sure, we have also the different exec data and exec address. We can simulate the transaction in tenderly, even if it didn't work.
And can I run like Gelato myself?
I did not know.
Like the whole thing. Let's say I like what you build, but you know I'm very security conscious, so I would like. Is it so open source that I can just run my whole thing
No,
myself?
well, all of the code is open source, but for the time being, we don't accept external node operators more than the ones that are qualified to execute the transaction. Thank you.
For the sixth time, going back to my setup. That was it. I
Yeah.
think we don't have any questions on the live stream, but if we do have questions for later, we are live streaming all day. And thank you so much, Javier, for coming again to do the workshop in person. We appreciate you. And until we set up the next speaker, we'll be muted. And thank you so much again.
Thank you.
And we are back again with our next speaker, Alex, the entrepreneur. That's his last name. Thank you, Alex, for coming in person. I forgot to pick them up for you. We will do it in 2 minutes. We know Alex because he came and gave a workshop at BUIDLEra Hackathon online, and it was the most productive workshops that I've ever seen. And on the side, I learned a lot of things about Alex that is like a genius person on code. So it's just a great opportunity for us to listen to the workshop and get some like information on security, right? Thank you so much for coming. And
Good to be here.
yeah, the stage is
And
yours.
yeah, my main goal with the workshop, as I showed my Twitter, is to basically give a bunch of ideas in terms of tools that you can use for security research. So the way the workshop was born was more of a like a buffet. I basically have a talk for 2 hours, and I'm just going to show you a few pieces. So at any time, feel free to ask me a question, or if you want to kind of twist some of the examples to tailor it a little bit to you. I think that's the best way, because at the end of the day, what I'm going to show is how I interface with a bunch of tools when it comes to debugging smart contracts, decompiling smart contracts, figuring out the tracing of smart contracts, although I'm going to just touch on that because it's not my forte. And then kind of the second part is going to be mostly related to the actual process that I follow in terms of finding bugs in smart contracts. So as you can see, I have a list here of these tools that I'm going to go over. And the first few ones is kind of more of an idea of how you could do open source intelligence, whereas the second part is going to be more of a hands-on coding. So at any time, again, feel free to let me know if you have specific questions. One of the greatest tools you have is actually on openchain.xyz. It used to be on the some website. But ultimately, anytime you find kind of a function signature that you cannot understand, obviously you could brute force it, or you can just, I guess, wing it. But you can just drop it here, and it's actually going to find you kind of an example. And this also works for custom errors. So like I grab a random signature here from Etherscan, and you can see that a function selector is just the first 4 bytes. So I'm just going to copy these. I'm just going to drop them, and I'm going to get the signature. And this is going to come in handy later because I got a treat for you in terms of decompiling smart contracts. But again, this is kind of a tool you want to always have in the toolbox. The second one kind of hits close to the home because I've been working at Badger for a couple of years and I consult for them. And this is actually the Badger Hacker. So there's this basically an address that actually performed the hack and tried to run away with the funds. And there's a bunch of tools that you can use. A couple of them that are, I think, are really interesting are breadcrumbs, and the other one is MetaZloop. But ultimately, they help kind of trace where the funds went. And if you spend enough time, you actually can build kind of a chart of where the fund went. And it's actually super easy to use. You just drop the address here. And it basically just works. It shows you all of these sources. That said, from my experience, especially when it comes to state level actors or this type of stuff, you basically always end up going to like centralized exchange, stolen identities, and that's where your OSINT ends. But at the same time, doing this kind of exercise can help you just kind of either learn about some of these setups in terms of hackers, and on the other end, it can also be helpful for your own privacy in terms of determining whether people can actually trace your funds, or certain people with certain level of knowledge in terms of funds, such as state actors or anybody. So I always find it useful. I feel like MetaZloop is more of the nice version where it looks really nice. However, from my experience, breadcrumbs is the one that works a little bit more better when you get really in the weeds of it. Maybe the internet is a little slow, but at the end of the day, you get this nice trace, and it can help you again figure out where everything went and can give you some ideas. Another thing you can do that I've actually was talking to developers at Aztec. I feel like it's actually reasonable. It's just it's timing attacks, where at the end of the day, if you always do something at the same time, or you operate your wallets in synchronous, people can basically kind of have an intuition, and over enough time, they actually can de-anonymize you. So that's also something you want to keep in mind. And again, this is more on the buffet side. This is something that I prepared just for you. I was going to show Panoramics, which is basically a bytecode decompiler. But I'm actually going to show you Heimdall, which is like the actual way to decompile contracts. And I'll tell kind of a story. Back in the Polygon yield farming days, there were a bunch of unverified contracts. Qidao had one of them. It was this kind of PSM deal where you could sell your token for 99 cents or buy the token for 1 It was unverified. And so back in the day, you would basically click a button down here that says decompile bytecode. That's the way you will do it. And then you'd hope that it works. And maybe you wait for a minute or two and either works or not. But today, I actually got a treat because I'm going to lick a random key that I got here on in Pura, or I guess on my Alchemy. But you literally just use this command here after you install Heimdall. Heimdall, decompile, address, RPC URL, and you paste the RPC URL. It's going to decompile the bytecode and turn it into Solidity, and it's basically going to show you like a translation of it that can help you understand how the contract works, and it can help you determine if this is a malicious contract or a contract that ultimately is just unverified under a benign reason. So I'm going to open kind of my workshop folder here, and I'm zooming in so it's a little easier to see. I'm just going to drop this command, and it's going to basically reverse engineer the whole thing, and typically takes just a few seconds, as you can see, and it's going to drop them in the output folder, and you can see that we have a decompiled.sol contract that we can now go and we can check. And obviously some of the decompiling uses hard-coded addresses, but again, we have the Samsung database here that I just showed you, so we can go back to open chain signatures, and we can actually, if we're motivated enough, we can basically rebuild the entire contract. In this case, it's most like a balance of operator. And so that can help us determine whether there are some rug vectors, whether there are some incorrect swaps, etc. And so this is a tool that when it comes to really understanding some of the work done by other people that don't want you to share it, it's really useful. So what I thought I'd do today, and if you have any question, let me know, but I just got an MEV bot. So I was like, let's do kind of an improvisation. Let's try and decompile a little bit of an MEV bot, see if we can learn something live on the spot. So this is actually the second best MEV bot, as in the second best by gas. Because if you actually to try and decompile the Jared bot, Jared knows, and so they actually built a bunch of strategies to prevent you from decompiling it, which I think is interesting. We'll show them that they're aware. But ultimately, we're going to basically do the same command here. So let me give this a shot. I'm going to delete the folder just for the sake of convenience. Actually, I'm going to just go in the terminal, Heimdall decompile. And then I'm going to put this address right here. And then I'm going to type --RPC URL, but we need to change it to mainnet. So it's going to be this one. So let's try this command right here. Again, it's going to disassemble, do its magic. And it should be this one. There we go. We ultimately have a contract that can teach us a little bit about some of the logic. If you notice, I thought it was really interesting because it's actually, like, I'm not exactly sure why this is done in this way, but the second I look at something like this, I immediately think of either binary search or an idea to basically optimize for gas, because you have less comparisons instead of comparison for exact match. So it makes me feel like there's some basically binary search going on. And this is basically the function called execute. Whereas if we go down, we'll see a more, let's say, a more easily recognizable function that is effectively allows to just perform arbitrary operations. You can see that this goes on for a while. The reasons why are multiple. This may be just an obfuscation technique. Maybe this means nothing, it's just there to distract you. Or maybe this is actually ultra complicated. Something we could do just out of curiosity would be to go and check on Etherscan some of these wallets, see if they are an EOA. We can see. So this ultimately seems to be a very complicated list of permitted addresses. And so it could be interesting if you spend enough time to actually be able to figure that out. But what every MEV bot will boil down to is a bunch of arbitrary execution and then a few checks for security. So that's what you're going to find if you dig long enough. But again, I just wanted to kind of give you the idea that all of the information is actually public, and through this tool, if you spend long enough, you can actually learn all of the secrets there. And if you want, we can actually do it for a specific hack. But I'm going to go into the next tool, which is Falcon, which from my experience is the best way to debug the transactions. In the future, there may be other tools, but I'm just going to kind of show the idea here. We got the Sturdy exploit. If you're not familiar with Sturdy, it was a lending protocol that allowed you to deposit, I believe, STETH, ETH, LP tokens, and then borrow ETH. And ultimately, it was manipulated because one of the Oracle reads did not check the reentrancy guard on Balancer, so or on Curve or both. We'll actually verify this by kind of showing you this process. So this is kind of the only aspect of the tool that we use in security research is really the call. But what we're trying to do at the beginning, when we kind of have no idea what's going on, is I'm just going to try and find kind of the topics. And so the first thing I'm looking here is kind of the flash loan area, right? I'm like, okay, there was a flash loan, so something was borrowed. And then I'm going to try and see the callback to the flash loan, because the second there's a flash loan, you know that everything below it is just a bunch of flash loan logic. And then there's going to be kind of the meat of the callback execution. So we're going to ignore everything until we find kind of the callback, which is here on the execute operation. So like everything that I'm showing here doesn't matter, whereas we are now in this execute operation section. We can see that WEF was received, right? We have two assets that were, I guess, borrowed, and then we have an initiator that is checked, and then we have this withdraw function just to get ETH. And then we have a call to the Lido curve contract, which is worth going to check in terms of its source. And that's because we want to, when we think about view reentrancy, we want to think about I guess, remove liquidity. And most importantly, we want to notice that ETH is the asset here. And so the second we know that ETH is the asset, because I've worked with Curve, I know that the first asset is always ETH. And so that means that when you withdraw, you can actually have the pool withdraw the ETH, which will change its virtual price. But then because ETH triggers the callback on the recipient, you can actually have a modified virtual price. And so that's where the intuition is at this point. We don't have proof, but this is kind of, again, showing you, applying the knowledge to the facts so that we can kind of narrow down the information that we have up until this point so that we kind of have a lead. And so this is what I'd be thinking about. And then I see a create here. But if you look at the trace, we're still on 5. That means that we're within the context of the execute operation, and we did the withdraw, we performed the add liquidity, and then we call create. So we're not within the context of this removal of liquidity, which has yet to happen, but we know that some liquidity was added. And so that's what I'm going to be thinking about if there's going to be a removal. But at this point, we simply have a new contract here. Anytime you're dealing with lending protocols, I call it a puppet. You basically will see a bunch of these accounts that are just puppets that are going to take bad debt. And they're there just to basically take on the shortfall of the lending protocol. So something you could actually do would be to label them as puppet or label it as puppet 1, fake 1, attack 1, and something that could be useful. But here we see a second account contract that is created. And we don't seem to see anything in particular there. And I believe that if we continue performing this set of operations, we'll eventually, there we go, we'll eventually get to a point where we have this contract right here calling Yoink, which is actually an unverified name, or maybe it is a purposely called name. But we will ultimately get to a point where in performing an exit right here, we see that we have an exit on Balancer on the call here. And then we also have a liquidation call on a specific address. So maybe this is when we would actually label it as, let's say, puppet 1. And so once we label it as puppet 1, we can actually check what is going on, and we can see that this address right here on the stack number 5, it basically liquidated itself, and that should give us again an idea around the view reentrancy. I don't think we have definitive proof at this point that that happened. We would most likely want to check at this point to see if that's the case, and hopefully kind of that gives you an idea of how you will narrow down to a specific set of incidents. At this point, like from what I showed you, it could still be two things: the curve price was manipulated or the bouncer price was manipulated. But if you follow this process long enough, you're going to get to a point where you'll determine which one it was. And then you'll also get to realize that one of the calls from the lending protocol was not triggering the reentrancy guard. So hopefully that gives you an idea of how you will debug this type of transactions. And from my experience, that's really how you learn. You learn from debugging this. Another tool that was mentioned to me during the event was Code's Law, which is basically really useful for us as security researchers, because let's say I found this exploit related to to the view reentrancy, then I can simply type get virtual price, and it's going to perform a query on the bytecode of all known contracts, and it's going to find every single call to that specific function. So this is still kind of a wide area in terms of determining if the specific calls are vulnerable, but that can be very useful because, again, it's going to allow us to, in the case that we believe the attack is replicable, it's going to allow us to more quickly find potential more victims so that we can warn them minutes after the first hack has happened, once we have determined the root cause. And the interesting aspect there is that we could actually unzip the solidity. I have a tool that I couldn't find to generate function selectors. I'm pretty sure you can do it on cast as well. But ultimately, we could also pass in the bytes version of the function selector here, and that can also help us kind of find unverified contracts. And then we could also apply some of the earlier advice that I showed in terms of determining some of the signatures or decompiling some of the unverified bytecode in order to determine, again, if these contracts will be vulnerable to such an attack. So that's kind of the first part of the talk was mostly kind of theoretical. If you have any question, let me know. Otherwise, this is where we go into more of finding vulnerabilities. And so the first tool I want to show is one that was built by the Coderina community.
That was supposed to
Yeah, go ahead.
So you just showed how you can input the function name and you get a bunch of verified contract functions matching that. Is it only a function name match, or do all the implementations of this function name are all also equal to?
I would believe that it will be only matching the name, but you have to keep in mind that unless you have a custom dispatcher on Solidity, then the name matching means that the underlying logic will match to a degree, because the name maps out to a specific function selector, and that's deterministic. So obviously each different pool may have a different implementation of the logic of the pool, but the way you will query it will be the same. So it's the same as saying that every time you see that specific call, it's as if you were calling a ERC20. You know that ERC20 will behave in a certain way. Some of the underlying logic could be different because it's rebasing, it has a fee, etc. But you're still performing substantially the same call. And I do believe it works on bytecode as well. I just, I guess I don't have a quick, let me see if I can give a quick example of that through the decompiled here. We're just going to yoink some 0x selector right here. We'll just see. I don't remember testing this, so we'll see if it works. If it doesn't work, the people at Electric Capital know what they need to work on next. Oh, there you go. It finds the matching logic, again, on verified contracts in this case. And maybe if you go deep enough, you'll eventually find non-verified contracts. But again, this is, in my opinion, it's the start of something really useful, which will be the idea of the have I been pawned database, where you just show some idea or some contracts that you interact with, and it shows you all of the list of possible exploits that have happened because of that integration with that contract. And so that can be a way to avoid repeating the same mistakes, which is very common in our space. And again, going back to not repeating the same mistakes, we have a tool by PyCode and also maintained by the Colorina community called Analyzer, which is basically a static analyzer that uses some regex and some AST to generate kind of a basic reports in terms of gas optimizations and in terms of basic findings. You can see the example on zkSync. It is fairly inaccurate in the sense of being too specific in terms of the specific finding it does find. But at the same time, it costs nothing to run. You literally just git clone, you yarn, and you use it. So let me show you an example here. Would be go in the analyzer repo. You have the contracts. You just in this case, I pasted a contract that I have. It's actually a yield farming strategy that I wrote that I found through Coleslaw, funnily enough. But ultimately, you basically will paste your contract here, either inlined or separated, and then you open the terminal in the context of analyzer. So cd analyzer, and then you yarn analyze contracts, and that's all you gotta do. It's gonna generate a report as report.md, and you can basically go through it, take some of the advice, such as caching the lamp, or your initializer may be vulnerable to a front run. There's the classic admin time finding. And what we found is that obviously most of the more interesting findings are not made open source. So what happens is this is kind of the skeleton of the system that you can use. And then most researchers will kind of add their own sauce, their own secrets, and they don't share that. But if you go on the Colorina website on colorina.com, just replace the A with a 4, you'll see that most contests have a known finding report. And so in the report of the known findings, which is typically here, you basically see that there's a few explanations. So I guess this is the one that doesn't have it. But the majority of contests will have a known finding here. And this is a type of report that is generated by a similar bot that uses AST and regex to effectively find hundreds of low-hanging fruits. And so again, it's a really convenient thing you can do for security research at that point. So at this point, we got into the spicy stuff. I'm gonna show you how I actually find bugs and stuff, and I'm gonna do it through a story. This is a story of a real bug that happened for What's Finance. So shout out to them, I guess. But basically, there was a specific high severity finding that was related to pricing an LP token. And the formula in which you price an LP token is actually fairly known. There's a famous Alpha Finance and a Simishal article about pricing LP tokens. But the problem is, if you try and use this formula to price a token that is a stable token, the invariant that determines the price of a swap is actually different. And so that means that this will actually break. This was found by Curious Apple, another security researcher. And so when it comes to using this formula only works if you have a x times y equals k swap, whereas if you have a x cubed times x times y cubed equals k swap, which is the stable swap invariant on Solidly or on Velodrome in this case, this will actually break. And so the best way to verify this is to know the math and explain it. But I'm going to show you kind of the brute forcey way that allows basically anybody to figure this out in a few minutes. So you will start by using Foundry. If you're not familiar with Foundry, just type Foundry book and then learn how to install it, but it's really easy. And once you've installed it, you want to perhaps add Open Zeppelin, but that's really as far as it goes. In terms of your setup, it's a really similar setup. And what we're gonna do is we're gonna only work on the test file, and we'll basically fork the chain. We'll build a couple of quick interfaces, and then we'll start brute forcing a bunch of swaps to see if we can actually break this idea of the price being stable. Because ultimately, when it comes to a critical severity, I mean, when it comes to proving that a system is safe, you need to formally verify that it's safe. But when it comes to finding a critical severity, you just need to find one example that breaks the whole thing and demonstrate a severe impact. And so it's a lot easier to break things, and that's why we can just, instead of fuzzing it, we can just brute force the whole thing. So we can start by going in the, basically I got a couple of interfaces here, and that's all we're gonna code, and then we're just gonna code some sort of a brute force loop. So the first step will be for us to get the formula that prices the token, which was in the BUIDLEra Oracle library in Phoenix. Choose here. And we can basically see that this is the formula. Get LP price, and the simplest way for us to continue here is just do raw, get the contract, src, rename, I will call it Velo Oracle. We'll paste it, and then we'll deal with the consequences of what I'm doing, because obviously it's not going to compile, but I'm going to show you how I cut everything short to make it so that it does. So first of all, we probably don't need the ERC token. I guess we do, but we have a different import, which is going to be from Open Zeppelin, and I think I already wrote the one. We got the Open Zeppelin import here, so we'll just do from lib/open Zeppelin -contracts, and this should be contracts token /ERC20.sol. I'm pretty sure we can just use the ERC20, although maybe they have the interface in the same folder. Yeah. So token /ERC20/IERC20. That's how we got the interface. The Velo pair, we probably just want to yoink from the project. So let's do that. So it saves a little bit of time. iVelopair.sol. We basically just yoink this. And for the sake of getting stuff done, we can literally just paste it up here. So now we have the interface for the pair. We're going to work on the Oracle. And in a couple of minutes, it's going to be working. Let's see. We no longer need the import. Let's see what Vima is used for. We need the nth root. So again, we go back to the project and we literally just continue yoinking math until we're satisfied. So in this case, we only need the nth root. But this uses fixed point math. But the reality is it actually uses math.sqrt because we only use it as the second root. So again, we're going to try and cut corners, because why would we import an entire project if we can import a couple of things? And that comes back to math. So this is what I'm going to do. I'm going to get this code right here. And I'm going to add it to the library BUIDLEra Oracle, which I'll eventually change to a contract, by the way. So basically, I have the nth root. I know I'm never going to use cube root, so I'm done there. And then on math.sqrt, I can just get the path, and then I'm going to import math from, I'm going to paste the rest of the path, lib/etc. And unless we're using a very different version of Open Zeppelin, this should be a decent starting point. So let's see the utils, math. Sounds good to me. So this is where we start compiling, and we expect the issues, obviously. That always breaks. So let's see what we got. First of all, we got this counter thing. So we just delete it. Get rid of that. Import Velo Oracle. Get rid of that as well. We already have the interface for the developer, so I'm removing that. We already have the pricer because we already wrote it. And so at this point, we'll change our contract, which is a library. We'll actually change it to a contract, which we'll also change the function to external, unless it's public. Just and also I'll leave it to public just in case, just to avoid going to change it again, but that should be it. So let's see again what type of error we're dealing with. Blah blah blah. File not found. Velo Oracle math. So let's fix that import real quick. lib/open zeppelin dash contracts. There we go. It's just the dash. And at this point we have vmap, but instead of vmap, we're simply gonna do the map that we already wrote, which is this. So nth root. So the way we sort this out is we get rid of this way, and that should be it. Okay, so at this point our contracts compile. We are kind of ready to attack at that level. So now we can just set up our test. We're gonna need to fork the chain, get an address, and then attack it. So any volunteer for a specific LP you guys want to attack? I can do WEF, STF, any preference there? Optimism scan. I guess I'm gonna go on optimism, and I'm gonna grab the WEF address. That's gonna be 1. And as I'm finding all of these addresses, the best thing you can do is to just comment them here so that you can use them later. We'll probably end up using a lot of this stuff. And then I guess we'll do STF as the second asset. STF optimism. I guess we'll do WSTF. Seems like it's not. Wrap liquid state ether. There you go. Once we have these 2 addresses, we can go in the Velodrome router. Optimism, Etherscan, Velodrome router. We're gonna grab the router so that we can get the pair. That's a fairly common UniV2 thing. And we can get the pair via pair 4. So we can do token A WEF, token B WST. We're gonna get the stable version. Let's see if it exists. There we go. Let's see what the TVL looks like. Although even if it's 50K TVL, that's sufficient to us. We can see there's it's actually fairly imbalanced. So it will be interesting to check how that plays out. But basically, this will be our stable pair. And then we can grab the unstable pair just in case, because we would expect that the stable version will break the invariant, whereas the unstable version will be fine. So that's also something we can look into. We can see that the TVL on the unstable version is, or the volatile pair is different. So at this point, we're going to need to fork the chain and get the specific token. So we have the function get LP price. So we'll set up our Velo Oracle here. I guess Velodrome Oracle. We'll deploy it here. And then we'll do test attack. We're going to have some balances, but let's just set up the basic test first, and then we'll add the balances. But effectively, our attack pattern is going to be to check initial price, then check a reserve, one of them, then do a massive swap, and then verify if price changes. That's basically our idea. So at this point, to get the initial price, we will do oracle.calculate LP token price on the get LP price. Get LP price on the LP token that we found, which is going to be this. So let's do address constant stable there. We pass the stable token here. And then in terms of prices, because of the fact that it's the same asset, because of the fact that we're looking for the invariant, we don't actually need to integrate the oracle, because if you were trying to verify one specific token, you would add the price. But in our case, we don't really care because we're just trying to see if the invariant holds for any pair. So at this point, we're going to register a array of prices. New UINT 256 square bracket 2. We're going to have price square bracket 0 equals to 118. And this is where, if you want to be super accurate, you could try and add like a different rate for WST, because arguably it's like 1.1, something like that. But let's just see what happens with this specific setup. So this will be our UINT 256 initial price. And then we're going to later check the reserves, because anytime you write something like this, you want to just see what happens, I guess, if it compiles, if it runs. And what I also like to do is I always open like a MD file so that I can check how I'm progressing. We can see that it compiles. Perhaps let's run a forge test. The test will break because we don't have forked the chain, right? So let's set that up real quick. Let me see if I have a alchemy key for optimism. So I guess the fastest way is to shield my GitHub and grab a repository that fetches historical prices on chain that I already had written. That will have the key there. And this is also the secret advantage of building your own stuff. You basically have everything already written. Right, so in this case, we need to go on optimism. So this is our URL. So I'm setting that up real quick. Good. With the key, which is this one. There you go. So now, because it took a while, I want to make sure that I never do it again. So what I'm going to do is I'm going to go here. I'm going to type forge test /RPC URL, and I'm going to paste the key, and I'm going to save this here so that I will never type it again, because why would I, you want to make sure that you're building your POC as you're finding stuff. So the way I typically do it is I call something like finding.md, and I'll always have like a boilerplate answer of this POC is written in Foundry. This is how you start the repo, blah, blah, blah. Because I'm not gonna, the second I find a bug, I wanna send it. I'm not gonna waste that time. So let's try and get the reserve, I guess. Let's see what's the most convenient way for us to do that. Is probably to grab, again, the interface on the pair and to check the reserves perhaps through this. Actually, I think the fastest way is to just get the balance of the reserve, because we know it's not manipulated. So we can just use this trick in our case. So trick, just get the balance of the P token since it's not manipulated yet, right? So that's what we're gonna do. UINT 256 initial balance of, let's say, WEF is equal to, and now we need to cast the WEF to a ERC20, so we can do, I feel like we haven't used it yet, so we'll just do a IERC20 constant WEF equals to IERC20 here. And at this point, we'll just check the balance of the LP pair. And so to do a massive swap, we're gonna basically have to deal the tokens. I got this quick cheat sheet here. This is how you deal tokens to yourself. You're gonna deal the WEF token to an attacker. So this is where I would also set up like a address attacker constant attacker equals to, something like OX bad. And at this point, we can rank to that. So vm.start rank. There we go. And then we would pass to them this amount. And I feel like to attack rationally, we would pass perhaps the entire reserve. That sounds like a pretty decent starting capital. And then obviously we could refine it later. But at this point, we have we're dealing this token. So let's do wef.approve on the stable pair for the amount because we are hackers, but we're still using limited allowances. And then we are going to simply do the swap by calling the swap on the router. So this is where I would have to grab the router real quick, which is going to be here. And I'm going to show you the hackiest way to create the interface. You just drop it here. iRouter constant develop router equals to iRouter of this address. And at this point, the only function we need is a write function called swap exact tokens for tokens. So that's literally the only function we want. Swap exact tokens for tokens. And this is how you yoink it from the code and you turn it into an interface. You just copy it, you drag it here. It's external, and you, I guess if it's an interface, you can do this. Whereas if you did it without an interface, you can just do this. And because you don't carry your fork in the chain, this is sufficient for you to work with most contracts in general. So that's something you want to keep in mind, is that most of the times, even if you see route here, we're going to go and check where route is, but route will probably boil down to address, right? It's going to actually boil down to this, so we actually need it. So let's import that as well. Address from, address to, and stable. So that's basically that. So let's do router, then router dot swap exact tokens for tokens. The amount in is going to be our initial balance. The amount out min, we're going to do 1 because we don't want to teach people to use 0. The 2 is going to be to ourselves, the attacker. We're going to use block dot timestamp. And we need to sort out these routes. So the way we're going to sort out the routes is, let me grab this real quick. Struct route. So let's do route memory r equals to new. This is a route, new route, and this is where I actually will just use Solidity by example. Honestly, anytime you forget something, just go and check it here. It takes 2 seconds. So the way you instantiate a struct is you don't use new, you just do the open parentheses, curly braces UI. So that's what we'll do. We'll do curlies from, and we're swapping from WEF, so address WEF, to, we're swapping into WSTF, which I believe is already an address, so we'll do casting later or whatever. And then in this case, this is a stable swap, so we're going to set it to true. There we go. Pass the route here. And I think it's routes, so it actually needs to be a list of routes. So we will do something like route, the route is equals to route, and then this is actually equal to new route square bracket 1, and then we set our square bracket 0 to the route. This is a memory entry. So hopefully that wasn't too confusing, but at the end of the day, we're just setting up some of the contracts to make that happen. We're missing a route square bracket. I guess it's an iRouter route because we pasted it there. So we just do it this way to make it work because we're passing it that way. Blah, 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 cannot convert. Now you can. And so at this point, we basically went through what is effectively an integration. We're seeing identical address, so we can debug with VDV, which is a good time to do so. But at this point, we're really close to effectively having set up our one instance of the swap. So the next step will be to basically add the fuzzer to perform that. Let me see. I guess I'm swapping for the same thing in this case. Maybe I messed up the addresses on the route. Yeah, so this was, we don't have a WST if. There you go. So that's basically what was missing. So at this point, we're going to have our swap, and it seems like it's going to compile most likely, and it's going to run. So we're just going to grab, I guess we got a weird revert on transfer from bad, maybe because we approved the wrong one. So let's make sure it's done to the correct address, which is the router, no longer the pair. And the last thing we'll do here is simply a UN256 of the new price. So let's just grab this code right here and call it new price. This is where we could do an assert equal of the initial price with the new price, and so say different. But the way I actually do it in most of my research, I will just import or just std console chew, because it's just so much more convenient. So what you will do, the way this is something I used to teach even in JavaScript, people always only log the value. We want to just do instead console chew log the name of the variable and then the value, and then even if you have 1,000 variables, you will never lose track of them. So that's what I'm doing here. But basically, this is getting us to an intuition of how the entire, I showed you the entire process and I did it live. And then we're getting an intuition as to how the attack is going to shape up, because at this point, the equation is unsatisfied. And so maybe I reduce the V by 1 so that I only check on my own logs. But this is where, the spider sense is tingling, because we're starting to get a change in the value, right? It seems like the value on the left, the initial price is 1.8, whereas the new price is 1.0. So we got to a very strong confidence that we made a swap, and the formula that the Oracle was supposed to use, which should have been stable and should be unchanged, has changed. So at this point, I can spend maybe the last 2 minutes in adding the unstable swap to see if that formula is stable or by what degree. But ultimately, at this point, we have built a POC, and my goal was to actually brute force it. So I guess I'll just do amount here, and we'll just replace. And this is how you do fuzzing or brute forcing in Foundry. You just add the variable in your test, and then you use it there. So this will be the random amount, and the random amount, you will just use it at the level of this value right here, because that's the value you're swapping in, and you always have that balance. So obviously, I guess we're gonna deal ourselves this amount, and there's probably a bunch of edge cases, reasons such as going into overflow of UN256, and for those reasons, I would always use something like 128 to avoid those. But basically, this would be a variation in which we are trying to see if we need a certain threshold to get to a point where this breaks, which is going to show us if the attack has a cost. We can see that in the case of the fuzzer, they put 5-way, and the price is already moving. But we will also argue that a change of 1-way is not significant. Whereas if we were to I don't remember if there is a threshold comparison, but I'm pretty sure we could do something like divided by, whatever precision we want. Let's say 1,000. So we only accept the difference if it's above 1,000-way, for example. And this is as simple as it gets for us to create this kind of brute force groups, so that we ultimately are able to demonstrate that with 26,000 ways of unit, we already have this type of an impact. Hopefully that shows you exactly how you find bugs in real systems. You go from an idea to an execution to actually a POC. And if you have any questions, I'd be happy to answer them. Or if you want me to show you something in the last couple of minutes, I'd be happy to as well.
Do we have any questions?
Amazing. So yeah, this is what you will do, and then you'd probably also check the. I feel like I have to at this point. I'm committed to this. I'm gonna spend 2 minutes and do the volatile pair. That way we can see that it actually works for that price, because obviously there is a mathematical demonstration that is supposed to hold there, and that would give you an enormous confidence in the fact that you actually did find a valid attack. And the simplest way for us to do that is obviously there is a better software engineering solution where you just write it better basically, but the hacker solution is this is test attack stable. We basically copy everything and we duplicate it. We have option shift down and you just do test attack volatile. And so now we have the test suite already working. I think I'll go back to the non-randomized values though. I feel like we want to just do the initial balance here. And then we will just grab these, what's it called? Unstable pair, I guess, the volatile pair. We declare it up here as volatile pair. And boom, boom. And that should be basically it. If you want to only run one test, you just do -- match test, and you paste the name of the test. And let's see, hopefully it doesn't break, you know, because this is gonna go in production soon. So hopefully we don't find some. There we go. It never breaks, and so and this was actually just run once. So this is when it doesn't break, this is when you actually are like, why is it not breaking, right? That's the first thing. So this is where we will do something like perhaps a fuzz run of a random amount, because in the other case, we found it immediately, so there was no point in fuzzing it. But this is where it does make sense. And if I'm not mistaken, you just need to change one setting here, something like fuzz runs 10,000. I honestly don't remember the name. But you literally just change this, and based on the setting, it will eventually run. And we can see that we're running into weird edge cases, such as insufficient amount, because we're using too small of a check, because we have the one out. So we will change it to 0. But ultimately, the fact that we are attacking at this level should show you that the attack on the volatile pair is kind of a high-hanging fruit, whereas the attack on the stable pair is a low-hanging fruit because we found it immediately. And so hopefully that gives you the entire context as to what you will do. And the last thing I would say in terms of tools, because I have, again, a million of them to share, but I'm going to conclude, is that you could also use Brownie or Ape as a way to build some of these pricers or some of your contracts as you interact with them. Because the main downside of that I found, at least with Foundry, is that if I use Chisel, I'm not going to be able to type something like router and have the contract automatically imported for me. And so that's where, if you are building your own contract and interacting with the chain, that's where something like Ape or Brownie can be very useful. And then to quickly shill other stuff, Parameter is amazing if you want to have ideas around some of the value and changes. So it's something you could check out. And lastly, anything that Trail of Bits has touched, you probably should be using in your production flow, because otherwise hackers are going to be using it to find exploits as well. I also have some basic honorable mention on the Solidity Visual Auditor. This is an extension that all researchers use, as far as I know, because it has the @audit tag, allows to determine the external input and internal inputs. And then you got the EVM codes and EVM storage, which I'm sure most of you are familiar with. But if you're not, as you start seeing POCs, you'll eventually be extremely familiar with them as well. So that's it for the talk. Thank you for attending, and have an amazing rest of your day.
We currently don't have any questions online, and I guess from the audience, everyone was like surprised for all of the technical things that you said. Thank you so much, Alex, for coming and for giving this great presentations. We will be leveraging from this workshop and use it everywhere we go. So thank you a lot for coming.
Amazing, my pleasure. And to all of the online anons, you're welcome. See you.
Let me just.
Sorry, guys.
Now we start for real. Well, we were muted on YouTube, so until I got some other people on the seats, that was my job for the last 2 minutes. Thank you, Nick, for coming on stage to talk on 1inch, the lead backend developer. Very good to have you here, and I feel like it's the first time that you're doing a workshop in collaboration with us.
I think so.
Yes, so very happy to have you and looking forward to have you more and all of the team also. Without further ado, now we can start for real and everyone is seeing you also on YouTube.
Great. So let's start. So as it was told, I'm Nick. I'm working at Foundation for the last 3 years. I participated almost at every product that we do have in the market. I'm going to talk about 2 main products that I have. The first one is a limit order, and the second one is Fusion. Basically, I just want to say that all of them are very linked to each other, so it's very bad to say, like to talk about specific one without talking to another one, and I'll show you the point later why it's like this. So, small recap about 1inch. Basically, it started at Ethereum New York in 2019 by a couple of people. I was there as well, but a several team. From 2019 to 2023, we have about 3 million users at DeFi. We are leading DeFi protocol right now, one of the leading DeFi protocols. We have about 300 billion volumes goes through us, for our protocols, our smart contracts on multiple chains. We are focused on EVM chains. We have about 70% of aggregation market share right now. One of our most successful product actually is a DEX aggregator, but right now we have several other products. Basically, one of the most interesting one compared to aggregation protocol is actually limit order protocol and the Fusion. Also, I want to say that we have a wallet and we have 1inch proper institutional, so we have actually a bunch of different solutions for different clients right now. So let's just make a small recap on this aggregation protocol. Actually, we do have a kind of Uniswap-like experience where we allow users to swap token to any other token, but actually it's a bit more advanced because we are trying to aggregate liquidity across multiple dexes. We are trying to find the best way, the best out path for your token to get max return, and we can split it across multiple dexes several times across multiple tokens. We can use multiple connector tokens. So, for example, if you're trying to swap 1inch to DAI, you can actually route it through wrap Bitcoin or wrap Ethereum to USDC, and only after that to the DAI. And at the same time, we are trying to use multiple other protocols. You can use 1inch limit order during one swap. All of that actually happens atomically. So that's how we started, and we just decided it's actually quite useful for any product that wants to integrate, and we have like atomic-like experience. Like it's just a one atomic transaction. It's very easy to integrate. A lot of partners are working with us. It's also available on zkSync right now. There is some statistics. I just made a screenshot like yesterday in the morning, so the volume is a bit lower. That is actually during 24 hours. We do have open analytics about all our protocols on June.com/1inch. So if you have any questions about what volumes do we have on which chain, what amount of users do we have, which are the most popular pairs, all of that is actually pretty open to everyone. So you can just use June Analytics to take a look. So just a small recap for developers, how aggregation protocol looks like and how it works. We do have basically an API for that because aggregation protocol is actually a smart contract browser where you execute transaction. You just need to specify the path for it. But to get this path, you need to ask our API for that. And it's in our API, we do have two handles that you need to use. The first one is actually quote that allows you to just get the quote of from token to dot token. For example, if I want to swap 1inch, I can call this API and get the quote, understanding the return amount. If I'm okay that it will be with this price, if I'm agree with that, I can call another API handle. It's a swap API, and basically just get the call data that I need to use if the transaction of user, basically. So it's kind of pretty easy just to have the APIs handles. Right now, I just want to say that we recently released 1inch developer portal for that. So if recently it was a big issue to use aggregation API if you want to have a launch it on your own project. Right now it's quite open for everyone, so you can just go to the Untitled Developer portal. We have a bunch of APIs there that can be useful for developers, not only aggregation protocol, but also limit order protocol, and almost every API that we use inside our team for our wallet, for our Z app. And yeah, so we have a free plan as well, so it will be easy for you to take a look. It's advanced documentation there. Actually, it's a first announce of this product right now because we didn't talk about it publicly yet, but we already made a shadow release. I think we will announce it a bit more public soon. So yeah, you are the first people who actually can take a look and try it and gather some feedback for us as well. So this is about some small recap about aggregation protocol, and let's focus on limit order protocol. So the first one, aggregation protocol, basically solves an issue when you want to make a market sale. When you want just to sell right now, like you don't want to wait, you want to get the best price. But what if you want to have more advanced like trading concept? What if you want to sell with a specific price? Basically, it's a limit order, and we actually launched the limit order protocol about 3 years ago. We have about 3 versions right now, and actually it's one of the most advanced protocols right now on the market, and I can tell you why. Because it's one of the most efficient on the market. The execution with the gas price is the lowest, and we do support multiple new features and new actually ways how you can interact with limit order protocol. It's just not simple limit order to sell your ERC20 tokens to other ERC20 tokens. Most of it, almost everything is configurable, because you can actually use not only ERC20 token, but you can use NFT tokens. You can also actually work with funds of the maker at anyhow. So let's start. Let's say that there is a user. Let's talk about concepts. There is a user. Basically, it's somebody who wants to sell something, create a limit order. What the user needs to do, basically, we just need to create a specific structure, basically an order with some conditions on that, and just sign that with your wallet using your private key. The second step, you need to submit this information with the signature to our API. And the next step, you just wait until it will be executed. Then the target price will be called. So this is the part of the user. And it's pretty easy to be as user actually on the Vanish. You can just use it on the front end side. Actually, we say it's a market makers. And there is another part. Actually, it's some entities that actually executes these orders of the users. Yeah, I can say that users actually don't pay any gas to create an order. It's off-chain computation, basically. You just share the signature and the conditions of this trade off-chain, and any entity that's okay to execute this transaction can actually get user's order and execute it from using Vanish API and using actually like any blockchain that supports limit order as zkSync, for example. So the strategy for any market taker is like that. First, you just searching across our limit order storage for the orders that are profitable for you. Let's imagine that, for example, right now I'm trying to sell Ethereum for 2,000 DAI. Let's imagine that price changed a bit and it's profitable right now for somebody. And I create a limit order, send it to the database, and like for example, in 1 hour, the target price called, and somebody just take my order and filled it and executed it with a bit better price. And the difference between this price is actually profit for the market taker. So it's quite good idea to execute limit orders because we have quite a lot of volume, and it's actually permissionless. All the rules are actually defined in the smart contract. But there is one more thing, that actually when you execute the limit order as a market taker, you need to pay for the gas. Basically, you need to understand that the difference between the price is also because of the market price and the limit order price when it is executed, depends on the gas price as well. Because it's also, we need to pay attention to that as we do an on-chain transaction. So there are two entities, maker and takers, that play with each other. That's actually basic limit order protocol. And it's like a small scheme how it basically works. So user doing like just signing orders off chain, and a taker that executes it on chain when it's profitable for the takers. We also use a limit order protocol combined with aggregation protocol. So if you're trying to swap on the market price, and we can see that there are some limit orders that are close to the market price that are profitable, we also execute them at the same time. So it's a kind of things that force together. Like as any DeFi protocol, they have a compatibility, so we can use both of them at the same time sometimes. Okay, so let's go deep into the source code. Basically, source code of the limit order right now is the same, is embedded into one each aggregation router. So right now we have a kind of one smart contract where you can see everything. It's open source. You can see it on Etherscan or any other chain. It's also available on the GitHub. So the main idea that basically, if you want to fill order, you need to think about several functions. We do have actually three functions to fill it. Depends on the type of the order. We do have two types of the order, but the default one is not RFQ. And actually, we do support permit functions. So if you want to make a limit order and don't pay for gas for approve, you can also make a permit for the token that actually supports the permit function and execute it. So let's talk a bit about limit order structure. This is basically the structure that you need to create as a developer when you're creating a limit order. Basically, there are some basic things like make your asset and take your asset. Make your asset actually the asset that you want to sell. Take your asset is asset that you want to get instead of the asset that you want to sell. You can specify the maker, for example. So if you actually maker is default your address when you who is selling the token. Basically, it can be not only externally owned account but actually any smart contract. And you can also specify the receiver if you want the funds to be transferred not to the maker address but to any other address as well. You can also specify the senders who will be allowed to execute the orders. So it's kind of useful when you want to have some P2P trades or like OTC-like trades on chain. And it's also making and taking amounts. Basically, the making amount, this is the amount that you want to sell, and taking amount is amount that you want to get instead. And there are additional data. It's a make your asset data, take your asset data. Basically, this is the way how you execute additional logic on top of yours. If it's not a ERC20 token, you just explain the protocol how to make a transfer of these assets. So because of that, actually, it's possible to not only using limit order for ERC20 tokens, but for any type of token like NFT token, like 1155 or 721, for example. And get making and get taking amount is actually the functions that allows you to specify the way how the limit order price can be changed during the different parameters. For example, you can say that if the volume is about 100 tokens, the price is like 100. But if the price goes down, like to 70, we can change the way how the rate will be going on this way. We do have a predicate as well. It's a way how you can actually add some additional conditions for the limit order. For example, we can specify with predicate. We can, for example, make stop loss limit order as an alternative for what we have on Sachs, for example. And we do have a pre-interaction and post-interaction functions. It's also like functions that allows you to do arbitrary logic if the maker funds before you execute your transaction and get these assets, gets this assets to your account, basically. The best example for it can be, for example, to unwrap Ethereum to Ethereum. So the user actually gets not a wrapped Ethereum, but real Ethereum instead. So basically, as I can say, you just need to call a fill order function, and let's take a look a bit on that. So you just specify a full data, signature, and as I already said, the signature can be not only externally owned account signature, but a smart contract signature. We'll go deep into that a bit later. And interaction, and making taking amount, and skip permit and first called amount. This is quite important parameter because it allows you to actually specify the threshold amount that is okay to execute for you, the minimum amount that you want to get on your account. So if the limit order is almost filled, it will be not interesting for you sometimes to execute it because it will be quite expensive for the gas price. So basically, the signature, as I already told you, you can specify it for smart contracts wallets. You can actually we actually proxy all the necessary data of the limit order to your smart contract, and you can batch them. For example, if you're using bonus multi-sig, you can verify that all the signatures for the limit orders are correct, and that allows you actually to create from multiple smart contracts, for example, from multi-signatures, from multi-sig. One more point that I can say that basically right now with Vanish API, with Vanish UX, you can't actually execute custom limit orders, but everything is open source, so you can just fork it and specify the additional parameters. And they're actually looking for any hacker to build their own protocols based on the limit order. It's actually audited, and it's pretty easy for you to fork it, and it's on the MIT license. So there are several examples that we do have in the repository, what you can do with that, that actually are not implemented on the UI. Let's focus a bit about predicate. That's actually the conditional execution that I was talking about before. We are using predicate by default to specify, to allow users to have a batch cancel of the limit order. This is a small issue because when you create a limit order and you send it somewhere, for example, the database, and it's very hard to cancel that. You create it, and it's free, it's gasless when you created it. But if you want to cancel that, you just need to somehow to say to the smart contract that this order is not valid anymore. To make it happen, we use unknowns. So when you want to cancel some specific limit order that can potentially be valid later, you just need to specify the unknowns, and you just make it higher, basically. And basic predicate allows you to actually just verify the knowns. And we also allows users, and the other one default predicate that we do have on limit order is actually timestamp below. This is basically the limitations for the interval when the limit order is valid. So this is like the default ones that we have on the front end side that is pre-built, I can say, but you can actually make any custom predicate. We do have like basically logic for that. You can use functions like add, equals, greater than, lower than, for example, for your predicate. And let's show some example for that. For example, I want to use a chain link oracle for DAI to wrap it to Ethereum to get the latest transfer using the smart contract. So basically, I just made an arbitrary static call for chain link oracle to get this rate. And after that, I can specify this predicate on limit order and saying that, okay, basically, if the price is lower than the price of DAI to Ether, let's actually not allow anyone to execute this limit order, or let's allow it to execute. Depends on the conditions, on the making taking amount and the making taking asset. So, for example, it can be a stop loss. The example will be on JavaScript, and today we'll be talking about like TypeScript, JavaScript functions, because mostly we are working with the limit orders on the front end side, and you're basically creating the limit order structures using JavaScript. We do have SDK for that. So let's talk about get making and get taking amount. So basically, by default, it's a default function that actually doesn't change, depends on the amounts, but you can also specify a custom get making and taking amount functions. Basically, let's talk about signature check. So we have several examples how you can verify the signature using not externally owned accounts, but some smart contracts, basically. And there are basically two ways how you can verify that. It's on-chain verification and off-chain. So you need to batch several signatures together, and only after that it will be valid. Okay, and let's talk about post interaction and pre-interaction again. Basically, for pre-interaction and post-interaction, the main difference between them is that pre-interaction is anything that you do before you start to execute process from function from the maker to taker. For example, if maker creates an order with one asset, and this asset is locked somewhere, for example, we can create a limit order and lock assets on Aave. So we get some interest rate. During the limit order, we can actually unstake these assets, for example, from there, and only after that transfer it to the taker account. So that's one additional plus advantage of our limit orders, that you can actually you don't need to lock these assets, but you create a limit order from the user. You can do whatever you want with them, but of course, if it's if the conditions of the limit order are not valid, it will be not executed. And it's a risk of the market taker basically to verify that this limit order is valid. Of course, if you use pre-interaction, this is the function that actually market taker executes, and market taker pays gas for it. So if it's a bit more complicated limit order, the price will be a bit lower, and it will be not that efficient sometimes. So you need to take care of that and understand the issues with the gas price. And another option is a post-interaction, how you can work with limit order. It's anything that you do after transfer of the maker assets. You can also do unwrap, for example. Let's talk about RFQ orders that we do support. It's a bit more efficient way to execute orders. So it allows you to fill order only once, because default limit orders allows you to fill order only any amount of time that you want if the conditions are okay, if the conditions are true. But RFQ orders allows you to do this only once for purely per the order. It's quite flexible it's not flexible for everyone, but it's more efficient. It's more efficient, more gas efficient. It's less features supported there, and we basically made it for the market makers. It's a bit more on public API, in public ways how you can create a limit order. So there are actually multiple ways how you can start working with limit orders. We have Vanish documentation, so it's a quick start on the middle, and there will be a real-life example. We do have a SDK for limit order. We do have a limit order protocol v3 on the GitHub available. Just take care and see that we have multiple versions there. And we do have a router v5. It's a deployed limit order protocol on Etherscan, so you can take a look as well if you need to check something. So I just want to say that the best way how you can try it is actually JavaScript tests. We have a library where we actually try to cover all use cases possible. And let's take a look a bit on that. This library calls limit order protocol utils. So basically, it allows you to interact with limit orders and don't think about the ways how you actually need to batch the call data, how you can actually interact with custom predicates through it. And it's public on NPM. And today I will be working with the TypeScript and Node.js, and I will just want to run some tests and to show you how you can build a limit order before we'll continue, because it actually is just a small, it's just the beginning. So let's basically around the structure of the protocol. We do have the main thing that we need to take a look actually is a limit order builder and limit order protocol facade tests. If you want to take a look at how we can make a limit order. So let's try to execute, for example, this test. This allows you to. That's actually a basic limit order with default with no any predicate, with just pretty mocked amounts. So this is basically the limit order structure that you have as a developer. And basically, the next step when you create something like a limit order, you just need to call an API that we have on public. I'll just show you the API on documentation. So you just specify the chain, depends on the chain. You just actually have several handles. And the post one is basically the handle to send your limit order to the database. And after that, actually, you're done. Our market takers will execute it if it will be valid. So it's quite simple. I just want to say that if it's pretty hard to think about the way how you can use different assets, not only use advanced tokens. And if you want to take a look on that, we basically want to get into the smart contracts. It's the right link, but limit order protocol v3. There we do have examples how we interact with NFTs, and basically you can build an NFT marketplace, for example, using a limit order. Actually, I want to talk a bit more about one more thing, and after that we will be coding. Okay. Basically, we just talked about limit order and aggregation API. And so limit order allows you to specify the price, the target price, but it can be executed on time. It's kind of sucks sometimes. And we have a market sell feature using aggregation protocol. And there are some issues there as well. Because when you're using something like market sell using on-chain protocol, like on-chain transaction as on Uniswap, we do have a MEF issues because users are sometimes front runs. Sometimes it's also a liquidity issue because it's very hard to accumulate this amount of liquidity over a short amount of time. And we decided to think about it a bit and think like, what is the option if you want to have a market sell feature, but we don't want to have it that atomic? What if user actually can wait a bit, like a couple of minutes, for example? If the price will be better, actually, I think almost any user go for it. So we decided that we were thinking about it, and we find an answer how we actually can build something that allows users to sell tokens almost with the market price, but not atomically, and with potentially gasless way and with MEF protection. And the answer to that is actually auctions. This is actually what we built recently. It's called Vanish Fusion. It's basically a Dutch auction that allows everyone to sell your token to any other token regardless. It's actually a combination of fusion of aggregation protocol and limit order protocol together. So it's actually a specified limit order. It's a custom limit order with additional conditions that allows us, like the resolvers of Vanish, basically to execute transaction during the auction interval. So why it's actually efficient? It's efficient because it's gasless and it's much more liquidity than just one atomic transaction, and protects users from MEF attacks. And also it's pretty the same user experience as we had before with the legacy feature. Let's go deep about gasless execution that we do have. Basically, it works pretty the same as the limit order. Users just sign a transaction. It's a specified limit order. Also share this transaction with our resolvers, with the database, and only after that, resolvers execute this transaction on the blockchain side. But as I said before, like as I already said, the limit orders part, gasless execution doesn't mean that you don't pay for gas at all, because somebody needs to pay for gas when they execute transaction. If it's another user, it's actually market taker, Vanish resolvers actually who execute this transaction. And of course, there is a price impact on the rate of the trade, but it's a bit more efficient than if you will try to make a swap individually, because Vanish resolvers can actually batch multiple user transactions into one on-chain transaction. So the gas price is a share between multiple users. Let's talk a bit about MEF protection. It's also pretty simple because actually, if you don't have on-chain, you don't have an opportunity to be somehow front-run by any arbitrage bots. But there is one more issue, because the persons who actually execute transaction, this is the resolvers, they can be attacked by MEF researchers. They can be arbitraged like front-runs, but we do assume that the professionals on the market who actually execute transactions, they are much more experienced to find the way how to protect from these attacks. So it's only for users, but it's only to users, but actually we do have an options, and so it's pretty easy to protect from MEF attacks especially if you're a developer or professional resolver, for example, using flashbots. And another point of Vanish Fusion that we do have, it's a limited liquidity. The main idea here is that, let's imagine a case, sometimes it's pretty common when users is trying to solve some large amount of shitcoins on some chain, and it's not enough tokens there to sell this shitcoin. And because of that, we have a pretty high slippage. And because we can't do anything when user create a transaction, you can't accumulate anything. You can't go to other chain. You can't go to the SEX and bridge your assets to this chain to have a better rate. Because of all of the issues, it's very hard. The seepage actually is pretty large. But in Fusion case, when it's a subject coin with a large amount of volume, actually it takes some time. And during this auction time, actually resolvers can, for example, accumulate this liquidity from multiple sources using private market makers, using cross-chain, for example, to reach the taker amount from somewhere else. And because of that, the market price will be better than it was using one atomic transaction as using aggregation protocol, for example. So the whole picture how Vanish Fusion works is actually almost the same as limit order, but we do have resolvers that actually executed almost on time. They have a constraints that are a bit lower than limit order. Like they have about 5 to 7 minutes by default to execute transaction at max. So we just share limit orders to the resolvers, and the resolvers just fill this transaction when the price is okay for them. But because of this is the auction price actually going down step by step, and that's why in the end of all, the resolvers are actually competing with each other for this transaction. And because there are multiple resolvers, it's in auction, the price will not go down too much, and that's why it will be one of the most efficient ways to execute the trade. We recently there was a test. There was 11,000 of Ethereum was sold through Vanish Fusion by Vanish treasury fund management, and it was actually executed better than on the market price because of the Vanish Fusion. So we already tested this solution with pretty large amount of volumes inside one trade. Okay, so what is the way to work with Fusion? There are actually two ways how developers can work with Fusion as well. The first one is as the same as limit orders. You can create a Fusion orders. So there are two alternatives. Depends on what your client or what you want. You can make a limit orders that are conditional. They have conditional execution that can be not executed in real time. And the Fusion is kind of the same limit order but executed on market with the market price because of the auction. And another way how you can actually work with the Vanish Fusion is becoming a resolver. So basically, you can execute transactions, and it's a bit more complex way, but it's pretty profitable because you just get the volumes of the users who are trying to trade on Vanish, and you just competing with other resolvers for the best price to offer the best price and execute this transaction. So we do have a Fusion SDK as well on the Vanish documentation. And actually, I have a small repo, it's called Fusion 1 that allows you actually to make a trade and to see your trade on the database and basically to specify the Fusion trade as well. What you need to actually run it is just have a private key and some assets on any chain where we do support Vanish Fusion. We will support Vanish Fusion on zkSync pretty soon. So let's take a look, for example, how to work with Vanish Fusion 101. I just want to, the most important part that you need to do, it's actually sucks, but every time you work with user assets, you still need to make approval. We do support permit function as well on most of the chains for most of the tokens that do support permit function. So in some cases, you don't need to pay gas to actually make approve, but you need to make a proof somehow to the Vanish aggregation router. That's actually audited about 11 times if you want to actually execute a trade on behalf of the user. So there is also a way how you can see how to make it using Fusion 101. So it's just basic approve your supply token to the Vanish aggregation router website. Just want to comment out a bit about it. There are some additional issues with that. If you will try to use it, you need to take care that the Fusion API works efficient on pretty large amounts. So if you want to test it, you need to test it at least with $100 trades. Yeah, sometimes it kind of sucks, but actually don't pay too much for gas. So you just need to use at least $100 and USD for any other token to make a trade. Otherwise, it will not allow you to execute it because it will be not efficient. You can actually force it to execute, but it will not have the same standard behavior as we expected. It's the same for any user. If the token price of the user is lower than $100, it's actually sometimes more profitable to use just on-chain transaction using aggregation router API, for example. So basically, if you try to use it, you just need to specify a private key and not URL that you will be using in the env file. And that's basically it. What you need to do. Let's take a look how you can create an order. It's basically about 20 lines of code. What you need to do is just install Manage Fusion SDK that's available on the GitHub, and after that, just call this function. Basically, what you need to specify is a from address to address, and then an amount. For example, you can swap on each address, like from on each token to DAI, and specify on each amount using wait, and specify the wallet address who will be swapping these assets. And there is a one more parameter called preset. This is auction preset parameter. And basically, it's the same logic as we have on the aggregation API. You first try to quote the price, and we will try to do this right now. And after that, you actually execute this price. So let's run it. 1 second. I hope internet works well right now. So right now we just execute the quote, and this is actually the body of the quote that API shows us. Let's take a deep look into that. So basically, the most important part that you want to see here when you get a quote is basically to see information about the presets that we do have. By default, using Vanilla SDK, you don't have a custom presets. You just recommend to have 3 options. The fast preset is actually a fast option. It's the most suitable usually for every user. The medium one and the slow one. The difference between them is the fees and actually the time interval and the moments when the price differs. And actually, we have a recommended preset by default using the API. It's the latest parameter here. As I can say, as I saw before, by default, recommended preset usually is the fast. And one more important parameter that you actually want to get between all of these parameters, actually, it's a 2 token amount. This is actually the return amount that you want to get. In this case, we are trying to swap on each token to the DAI. So let me just see the total amount that we are trying to swap. So we are trying to swap 100 on each tokens, and we are trying to swap it to the wrapped Ethereum token, as I can see. And let's try to understand like this amount, just reverse it a bit. So to make it happen, we just basically it's in the way. So if you want to see that how much Ethereum actually will get, you just have to divide it by 10 multiplies 18. So this is the amount of wrapped Ethereum you will get by getting this quote. Let's double check that we have put the same response on the API, for example. So as you can see, the response amount is almost the same. It depends on the market conditions of the state, so it can differ a bit, but there is no any mistake. If you will try to learn using Manage Fusion, you can just compare the quote prices with the front end, for example, of Manage. So you'll be sure that you don't have any mistakes. So as a developer, if you want to start is a quick start. Basically, you just need to have a 2 token amount information from the code. And if you're okay with this 2 token amount for the user, basically the next step for you is just to get 2 token amounts. Like actually to understand that it's okay, you just get the preset from this parameter as a recommended preset. And let's get back to create order function. So you just specify again, like from 2 token amount and the preset parameter. And basically, when you specify the preset parameter and create our order function, that it just sent to the API. And after that, actually you are finished. You will get information about the transaction for the order ID for the Vantage Fusion auction. And after that, you can actually take a look on that by using additional functions to watch it. It's orders by maker function. Let's just take a look on that as well. Basically, I think that the issue that with me is that I don't want to show you my private key. I don't have it in V right now, but you do need to specify your public address to get the orders by maker function. So you get your orders. Right now, I just don't want to do it on the like using a screen view. But when we have a private key on the env file, you'll get a list of all your functions of all the orders, and that's actually what you want to show to the user when you're integrating Fusion API. So this is actually a quick start how you can use Vantage Fusion as a developer to make swaps. But there is one more thing about how you can execute, how you can run Vantage Fusion as a resolver. Right now, we don't have a Vantage Fusion one-on-one for resolvers, but there are some useful examples on the website, on the documentation. We do have actually, on the GitHub, actually, we have a resolver. We do have kind of Fusion resolver example that actually allows you to see how to execute the funds by default. If you would try to be a resolver, that's one of the most useful repos for you to take a look. Basically, what you need to do is pretty the same as on limit order. You just need to execute a specific smart contract function with the assets that you and the limit order ID that you want to execute. And you can also take a look on the test, of course. Basically, the example here is that you just you just actually called this function. One moment. Basically, it's a settlement contract. You just encode. You call settlement contract to execute the limit order, like the Fusion order here. I see that the time is almost closed right now. I just want to change to I just want to ask some of your questions maybe, because maybe you have some of them about Fusion or limit order.
So to cancel. So to cancel limit order, I guess I have to send the request to change that, right?
Yes. The only way to cancel limit order is to increase the nonce on your address on the smart contract. That's why it happens because when you create a limit order with the signature, the smart contract just verify the conditions and your signature. But if the conditions actually are okay, but you want to cancel that, we can try to delete this data from database. But what if somebody already get it from it? And in this way, it will be kind of painful experience because it looks like you cancel it, but somebody actually executed it later. The only safe option is actually just to increase the nonce on the smart contract, so we can actually cancel this limit order. You basically can cancel multiple limit orders at once. For example, you can increase nonce not for one, but for a bunch of the limit orders. It's more advanced right now in our case, so it's a bit more better user experience right now, but it still sucks because you need to pay for gas. So when you create a limit order, you need to think about how correct it is. We do have some protections on the user interface, so you can't create a limit order that will be not profitable or like not will have extremely bad price. So if the price slippage is like much more lower than we have on the market price, you will not be allowed to make it on the UI as a like dump protection. But as a developer, you can do whatever you want. So you need to be very accurate when you create a limit order and understand the conditions of it, basically. Because there is also no guarantee that when you cancel the limit order, it will be canceled faster than it will be executed. Because somebody can front run you and outcompete you just
cancellation.
run it.
Yeah.
You mentioned earlier that you want people to build on the limit order. And I think you mentioned like you can make an NFT marketplace. Do you have other ideas for what people should be building or something that you're excited about personally?
You can actually use limit order, for example, use it for liquidations, as an example. It's possible to have basically, it's possible, for example, to use it for derivatives, for perpetual trades as well. I think some of these concepts it's pretty a lot of fun, and it can be pretty efficient because, as I said before, right now we have about 80% of the market share, and the most important about limit orders is the gas efficiency. Because when you have the same trade on multiple limit order protocols, the first one will be executed. It will be, for example, the best one will be the first who have the better gas price execution for the taker. So I think it will be quite efficient to have something like perpetual swaps using limit order, for example. Yeah. Actually, I just want to say that Vanish is also sponsored the Ethereum Global event at Paris right now, and we will have a nomination, and have a prize. So everyone who wants to build a limit order using, for example, zkSync as well, we will be happy to. We have a prize pool for that. So every hacker, you are welcome to join Ethereum Global and hack with us today, in a couple of days.
Well, thank you very much. Thank you, Nick, for coming and doing the workshop. And for the audience, we will prepare for the next workshop by Nick, software engineer who just joined our DevRel team at zkSync. So stay tuned for that. We'll come back in a few minutes. Thank you.
Yeah.
And we are back with another workshop from Nicholas, who is part of our DevRel team at zkSync. He just joined the team as a software engineer, and very happy to have him here at ECC, with BUIDLEra Developer Day, with another workshop. So thank you, and thank you for coming, and the stage is yours.
Perfect, thank you. So today's talk is going to be about an alpha release that we're announcing today called the in-memory node for developing and debugging. And I'm going to go through a few different things during the next 50 minutes, 55 minutes, I think is what we got. I'm going to talk about how do we test today for developers that are deploying smart contracts to zkSync era. What is this new in-memory node? How does it compare? When would you want to use one versus the other? And then a bunch of demos and examples going through the features that we have released with it. And finally, talk about what's next. This is an alpha release, so what is missing and how are we going to move forward with the community. So as the intro from Alpi stated, my name's Nick Villanova. I'm on the DevRel team for zkSync Matter Labs. My handle is right here. Feel free to reach out to me on Twitter, GitHub, etc. And let's just get into it. So testing today, really you have two options. The first is the testnet, zkSync era testnet. It's a public network that is deployed on top of the Goerli testnet. The funds are not real. And this is typically what you're going to see with every tutorial that we have, right? Whenever you get started. This is the issue that a lot of engineers run into whenever they first get started is just getting the funds from a faucet, right? That is really kind of a complicated process sometimes. And that's why we also have the second option, a local network. And so this is based off of this GitHub repo that you can go to local setup. And what it does is it spins up 3 Docker containers. The first is going to be a Geth node. That's your layer 1. The second is going to be a zkSync node. That's your layer 2. And then finally, a Postgres server. So this is going to be the database behind zkSync. To get this up and running, let's say 5 minutes, just pulling down Docker images, getting it up and running. It should show up, start running with Docker Compose in the correct order. If you run into some issues, it might be a little bit more than 5 minutes, but let's just say that's the time. So this is sort of the world today. Another small footnote about the testnet: we are looking into migrating to Sequoia as an alternative to Goerli, but it's a similar idea of a public network that you're going to be able to use on something like MetaMask or whatever wallet. So that's long description of what we have today. That's not what we're here for. What we're here for is the in-memory node. And this is something that is already in existence for the layer 1, which is provided by Hardhat, where they have like a network, right? So if you're running Hardhat projects and you're running in local tests, it's going to spin them up in-memory node for you already. You don't have to deploy Docker containers. You don't have to reach out to a public network. It's all running locally. So what do you get with this in-memory node that we have for our layer 2? Well, one, it's going to start up fast, right? If you are just starting it with no extra commands, and we'll go through those later, that's less than a second, and boom, you have a local network. Number 2, we allow for forking of the networks, the mainnet, the fastnet, another custom network that you might have running even locally, but at a specific height. I'll talk through that later. Replaying existing transactions, right? So I've talked about testing locally, but there's also the debugging piece of this. So we'll go through some great examples later. Pre-configured rich accounts. Whenever you have a local network or a test network, having some accounts with a lot of ETH is just makes life easier for validating whatever you want for replays or transactions. And then finally, for the debugging piece, call stacks, and console logs. Being able to easily access these and making them just approachable for the debugging of a smart contract. So today, if you want to run this, you have to clone the repo, go in, run make all, and then now you can just run the node. So that would look like, era test node run. So that's pretty much it. We're looking into ways to make this a little easier, but for now, this is the alpha release, and this is what it would look like. So let's talk about what are the comparisons. I've talked about those first two for a little bit. Why would you use the Docker nodes over this in-memory node that starts up so fast, right? Well, as you compare these three, you see this. I just picked like 4 main topics to go through. One, running things locally, right? So that testnet, that's great if it's up there, but you don't want to always integrate that with CI, right? You don't want to have to wait all the time for the transaction to occur, or the cost for making sure you have enough Gorley ETH or a faucet that you have access to. So that's why you would have a local setup, whether it be in memory or rich accounts. Right? Hey, I just talked about having access to these tokens. Yeah, with local setup, we do also have rich accounts, and same thing with this in memory node. But then we get into the third column, the fast setup. So yeah, getting the Docker images stood up, especially if it's just from scratch for like a CI test process, that's gonna waste time. I'm talking minutes. Whereas using the testnet, you can just connect to it. It's always up. It's pretty easy to connect to. It'll take less than a second. Same thing with the in-memory node. Getting it running, and if you want to connect to it, that's less than a second. Finally, the thing that's really missing that you really get is the debugging piece of the in-memory node. I'm going to show you what it's like and how much more information you can get by having this in-memory node running locally and deploying smart contracts, replaying transactions, all these sort of things. What more information do you get just really fast right in front of you? Right at your fingertips. The other thing I want to cover is sort of the configurations of these. This is a public network, the testnet, so that's the RDC URL. The other two, these are going to be running locally, so those are the port numbers. 3050 if you're doing the Docker setup, but the new one is going to be running on 8011. The chain IDs are different. We want a different chain ID. I can talk about that a little later, but why that is. The main thing to note right now is there is no layer 1 whenever you're starting this locally. It's just all layer 2 stuff. If you need to validate all the way back down to layer 1, you're going to want to use the full Docker setup. You need that layer 1. This is room for improvement, but for now, this is what the state of the world is. So let's start going into demos and showing you what it's actually like. What I'm going to do is walk you through the basic reader contract, and I'll explain what that is. But the one thing I want to cover before going into VS Code is the main change that you really have to make inside of Hardhat. I'm going to be using Hardhat today. Is just changing the URL. Right now, if you're doing the local host network, it would say localhost 3035. Just change the port to 8011, and that's all you have to do. To run the node, just before I get into this, it is this run command. I believe that gets it through the demo. So what I'm going to do here, let me know if I need to. Yeah, let me zoom. Cool. So for those who don't know, we have a CLI tool called zkSync CLI. And what this does is gives you some great commands that create just basic templates for you. And so I'm going to create a template called Hello Bears, and it'll be Hardhat Solidity. And what it's doing is creating a folder with just like an example. So I don't have to like copy and paste. And if you're a new engineer or a new developer to zkSync, this will get you started on the right path. So in here, you see that it has created a new directory. Hello, Paris. I'm going to open up a new VS Code over there. Instance. I'll get this set up. All right. So what is in this repo? Or sorry, in this folder? This is the greeter smart contract. It's just a getter and setter, or a private string, and that's right here, the greeting. Whenever you construct it, you give it an initial value, and then there's greet and set greeting. Nothing too complicated. What we're going to do is, first thing I want to do is compile the smart contracts for this folder. Yarn hardhat compile. In the meantime, here is the package.json for running commands. Since I am just doing everything locally, I am going to copy and paste this node environment equals test because I don't want to keep typing it over and over during this presentation. But like we had talked about before, in hardhat config.ts, there was already this 3050 for using the Docker container endpoint. I'm just going to change that to AWS. You don't really have to pass in anything greet network. I'm just going to leave that there. That would be the layer 1 endpoint. I'm not going to use that. Cool. So let's go ahead and this has already compiled. The two commands that I'm going to be going through are deploying greet. So deploy will actually deploy the smart contract. Greet will use it, and I'll talk about that as we get there. So what we'll do first is start up the node. Take these up here, everyone can see. So here at test node run. Whenever I run this, you see it's already started. It has 4 rich accounts, each with 10,000 ETH in here. It is a very similar format to if you've run the hardhat, in memory node. This is what it looks like. It tells you what it's running on, what ports, what the chain ID is. So if you need to connect to it, that's it. But it's up and running. So let's take a look real quick at making a private key for our deployments. What I'm going to do is copy the env example and then take this private key for rich account number 1, save it here. So whenever we go into our deployment scripts, it's going to pull up this key, and what it's going to do is deploy the greeter contract and initially set it to either. Cool. Really not much else to this, but we will get to see what this looks like. Space. So as it's deploying this contract, you see right here, this is where it executed this transaction. Let's walk through sort of what you see. So 1, here's the transaction hash. You see the status of this transaction. You see who initiated it, who was the payer, how much gas was used. Right now, we're hard coding the gas limit, but we'll update it in the future to be able to configure it to whatever you want. There are no console logs. If there were, show up here. There are a bunch of call traces. Those are fun. We'll get into those in a little bit. But then you'll also see right here, these are events that show up on the stream. So this is basically just streaming out all of the requests that are coming in. Now, the output from this deployment script gives us the address for the smart contract. So what we're going to do next is let's try and use it. So we have another script that is using this smart contract. So I'm going to take the address that was returned from down here, console output, and I'll sort of walk you through basically what's happening. What it's doing is it's gonna connect to the contract. It's gonna call greet. It's gonna call set greeting with, I'm gonna change this, fellow pairs. And then it's going to get the greet again. So you'll see what it was before, change it, print it out. What does that look like over here? How we do it. So as we run this, you see it already finished. It was hi there. And then it updated, and here's the hash. And then here's the new value. Over here you see, well, there is a call for success. That was getting it the first time. Here's the transaction where we updated it. And then here's where we got it the second time. So you can see that it's working, right? It's pretty fast. One other thing that we want to do, just to show you real quick, is there's another command in here, right? There's test. So as part of this project, we also have, these mobile try tests. So what this does is it will deploy the contract. It will basically make sure that it's set to high, whenever it's instantiated, updated to Hola Mundo, and then make sure that it's been updated. So what does this look like from an user perspective of being able to run tests locally? There you go. This works, right? Really fast. One of the things that has been implemented for now is one transaction per block, right? So it's just going to keep chugging through. We'll make it so that it's more modifiable in the future, but for now, for testing, like that's majority of use cases that we're trying to address right now. Cool. So we've talked about starting this node. We've talked about deploying contracts. We've talked about those rich accounts. We've talked about executing the contracts and then even running automated tests. These are all things that we can do with just the basic run command. But let's start getting a little fancy. Let's figure out what is that debugging piece that I talked about earlier. We want to talk about call stacks and console logs. One thing we realized, a lot of these contracts rely on console logs for debugging. It's like the go-to for trying to figure out something that has gone wrong. So let's make sure that whenever you run, you can see the console logs. So first thing we want to do is in set greeting, I'm going to add some. Okay? In fact, you see in here for hard hat, they have console.log. So I've added these two statements of set greeting called and then whatever string you gave it, print it out. But I've also added a little something in here right underneath, which is a check to see if the string is equal to, or the hash of the string is equal to test, then we want to throw a revert, right? We want to, I'll show you what that looks like from inside of the node, but we want to be able to test, or I want to be able to show you when a revert happens, what do you experience from this in-memory? How much information can you gather? So those are the quick updates. I'm going to do another compile and then redeploy this updated contract and there we go. And deploy this contract. Perfect. New contract's been deployed. Let's go into whenever we use the greeter. That's the new greeter, right? Has the console log, has the check to see if it's test. So let's run it. You see right here in the set greeting, the console logs show up. Pretty simple, straightforward. It's just streaming out with everything else. It was a little difficult before to show you hey, there are no console logs, it's empty, but you see them, they show up. Cool. But then we get into an interesting example of, I put that check in there. What happens if I try and set this to test? Right? Well, from this command line, you don't really see. It gives you a bunch of just unreadable crap. Nice way to put it. But from the node, in the current just plain run, you'll see the transaction failed. You'll see the events. But what you really want to see are these call traces. So let's start showing some calls. So what we want to add here is show calls all, and then resolve. All right, so what did I add? These two flags right here. Let's talk about show calls first. So show calls is gonna take this set of call traces, these stack traces. So they're going to start being displayed. It's gonna be a lot more information. It'll have the addresses, it'll have them indented based off of specific order. Go into that once I can show you an example. But then it's going to do that for the system contracts, the user contracts, etc. Resolve hashes is going to take these addresses and make them more human readable by reaching out to the OpenReach API to do so. So let me show you what that looks like. Because I have restarted this node, I have to redeploy smart contract. You see, now that I've deployed, things are a little slower, but it gives you access to so much more information. This was deploying the contract. So you start seeing all of these call traces with human readable names where we can find, oh, we needed to get the chain ID, we needed to set the transaction origin, get gas prices. This is everything that's happening behind the scenes. You can even see right here, the create. And this is where we have the hash that eventually gets returned as part of the one command. Finally, you also see in the events, there's more information. If you needed to really dive deeper into the full value of some of these events, it's here. It's a little more difficult to read, but it's all here if you need to debug it. So let's try and run this reader again with the test value and see what happens. Well, you see these reverts show up bright red, right? You can see that it reverted, and that's that received test value. That's what we had put as the reason, right, for this revert. But you can see everything that led up to it. And you can also see, all right, we had some console log statements. We had the two pickaxe to compare the hashes to make sure test is equal to the string, et cetera, et cetera. But you get the whole stack leading up to this revert, which is huge as you're debugging. And there are many use cases for this, and I'll start going into this in a little bit. So to go back to what we sort of saw right now, we are getting the console log output. We are seeing the call stacks. We are seeing readable events and the ABI functions by reaching out to OpenChain. And the errors and reverts are so much easier to spot throughout this entire substack. Your eyes just go to it and you see where the problem is, and you can debug faster. That's the idea. So let's talk about forking and replaying transactions. So up until now, I've just been doing the run command. Right? It's just starting from scratch, like that's block 0, go. But we had, let's say in this example, a customer reaches out and they say, hey, within our test, everything works fine. But zkSync has issues when some transactions fail with an error message. Here's a contract address. I tested it myself with the same result. If you need any more information, please let us know. We want the ability to be able to take this transaction, replay it against the network as it was for them. And we want to be able to do that with this in-memory node so that we can see the stack trace and we can see as much information as possible locally. So let's take a look at this contract. So here it is. basically, you want to let's just take a look at the first transaction and let's try and replay it, right? I mentioned that's something that we can do. So what does that look like? In running your test node, we've already shown you these two flags, but then instead of run, what we're going to do is replay underscore tx. We're going to say, hey, replay this against testnet. What it's going to do is fork the testnet to your local, and then run this exact transaction. So you can replay what they did. And let's look at what that looks like. All right. So we took that transaction hash and we start replaying. We see, hey, it actually forked testnet. It's executing the transaction. I believe there were like 2 transactions in this one. Everything's running fine so far. 3 events, nothing abnormal. Then we start going into the second execution. There we go. We are able to replicate what they have or what they experience. Here is the panic error. Here's the revert with unknown revert reason. And here is the entire stack trace that sort of led up to that point. Not only that, hey, the node is actually still running. Right? So if you want to replay things on top of that, you can. If you want to dig deeper and look closer at the node afterwards, you still can. But that is a prime example of replaying a transaction and working that is really invaluable for debugging, especially when the network is not yours. So forking, right? I talked about that. Well, what if I just want to fork? I don't want to replay a transaction. You can do that. Yeah. The fork command. Not only can you do that, you can fork at a specific height. So fork at 7 million. I can read numbers. 7 million for testnet. So you run that. And there you go. It will still add the rich counts on top, if you want to mess around. But what you see is, oh, here's the batch number. And if you were to look up, all right, right here. You look at this block and you see, oh, there's the batch. It matches, right? Just to show like, hey, this is actually going down the right stuff. And you can fork at a very specific height for testing purposes locally. And like that was pretty fast. And then time it, but I want to say it's like less than 5 seconds. And you're done. You're ready to go. So what did we see? We talked about forking. You can fork mainnet and testnet. You can fork at a specific height, and you can replay transactions. MetaMask. Yeah, this is a fun one. So getting MetaMask to point to your local in-memory node is possible. Let's talk about what that looks like. So what I'm going to do is just run it normally again. And over here in MetaMask, I have running. Whenever you have networks, you can just add a new network. Do it manually, right? You can call it in-memory node. Going to point it to my local host, 8011. If you ever forget it, it's right here whenever you start up. And you can see it's already connected because it's telling you, hey, chain ID with match, 260. And it'll be cool. Switch to the in-memory node. Yeah, I just did run, so there's like nothing in here. None of my accounts have anything. But what I can do is, I know these rich accounts exist and are created. I'm just going to take this private key, import it. There you go, 10,000 each. You're showing up, you're good. Let me add the other one too, the second one. And another thing to point out is it's really great to have these rich accounts, not just for testing, for presentations. You saw in previous presentations, people are really scared to ever show their private key. You don't have to be scared to show these private keys, right? Like, it's not a problem. They're for testing. It's only on this level node. You're fine. I can show you these private keys all day. So So let's test sending, right? Let's say a rich person account 0 wants to send it to rich person number 1, and they're going to send 300 ETH. I probably need to disable that because MetaMask likes to show me little notifications. But while that's going on, you see all of the commands that are coming through from MetaMask while that's happening. In fact, I can do the same debugging trace flags, and you can see exactly what MetaMask is trying to do. Sometimes, or what the website is telling MetaMask it's trying to do. Whenever MetaMask does a new launch or updates its Chrome extension, you can see what's going on, if anything changed. But you see, yep, all right, you're down less, about 300 ETH on this account. Go down to the other rich account, and there's 300 ETH richer. One thing to note is every time you restart this node, right, MetaMask is holding on in memory to a nonce for your accounts. Right? So what you have to do is go into clear activity. So every time you restart the node, you want to go in here and clear this activity tab. If you don't, it's going to show previous transactions from whenever you stopped the in-memory node from a previous time. But let's say you ran it again and you forked mainnet instead of testnet, it's going to freak out and be like, I don't know what you want me to do. And it's not going to be happy. So just go in here, clear activity tab data, and you're good. So I showed you how to connect MetaMask to this in-memory node, transferring funds, and then gave you the warning of always resetting your data. Cool. So what's next? Well, there are a few things. This is an alpha release, right? We did the bare minimum of APIs that we felt comfortable with to make this release more public fashion. So there are a lot of things that still need to be implemented. There's a lot of work that needs to be done. But the basics work, and we're still going, validating. Our tutorials are mostly working for this. We are just having to write more code, right? It takes time. But the basics are working. I showed them off to you, right? And that goes hand in hand with growing with the open source community. This repo is public. It's open source. If you want to add a missing API, that's great. It's pretty easy to pick up, and we're like really active on this repo. Another point is integrating with hard hat testing API. This idea of an in-memory node exists with the hard hat project. That's their network node. But imagine a world where if you run hard hat, what if it actually starts up not only the hard hat's network node as the L1, but then starts up this node as its L2. And now you have an in-memory L1 and L2. And you have full access to everything in between. Then you also, if you expand the APIs, you get access to things like, let's see, I had it in here. The accounts, impersonating accounts, sorry. Yeah, you can impersonate accounts, which is huge, that a lot of people use with hard hat testing. You can theoretically take this is built in Rust, and you can assemble it as a WebAssembly package and include it in JavaScript if you really want. With things like impersonating accounts, or even having the ability to increase and decrease the node time, this allows you to test things that were previously untested. Things like testing staking and loans, like that is something we've been asked to provide some solution for. And if we can control that node time, that gives them the flexibility to be able to test these things in even like unit tests, and it'd be like super fast. Yeah, join our developer community on GitHub. I know it's a link, so maybe we'll post it in the YouTube chat in a little bit. But yeah, it's here. We have moved a lot of our discussions on there, so anyone who runs into issues or is asking for features, we want to be able to like stack rank what is the most important APIs that we're making. What is the functionality that, yes, our tutorials might work or our examples that we've developed internally work, but if it's not working for you, we want to know. Yeah, this is thinking. And this is our QR code for the events that we're doing this week. Obviously, we're going to be here on the 7th floor, open workspace for the rest of the week. And you're more than welcome to reach out to any of us. But yeah, any questions?
I have a question.
Yeah.
Sorry, I can't trouble with my voice.
You're fine.
What about L1 integration? Because I saw you send a message to L1 when you were like putting the address that, because I think you used to have one repo where you can run a local node, the repo in Rust, the era dev repo or something like that, and you were able to connect that node to L1. Should you be able to connect this, or you have to do some work?
If connecting it to an L1.
Yes, for example, in the Docker container.
So the Docker does start L1 and L2.
Yeah.
Right. The local node doesn't. The local node. The idea is that, well, like what Niklas was talking about when we were starting the in-memory node, we wanted to focus on the case of like, hey, it's stuck in L2. We want to run it. Let's build it fast.
Okay. Yeah.
And in the future, we are, and this is actually the thing we need people's help, is we could start GAF and this in-memory node and connect them or not. But this is something that we didn't get to.
Okay, perfect.
Yeah. Sorry.
We don't have questions from YouTube live stream, and if we don't have any more questions, thank you so much, Nick, for all of the details and for testing environment now that we have with the local node. This is so exciting for all of the team and for all of the future developers who will build on zkSync. We'll get back with another presentation in 5 minutes for everyone who's following us online. Thank you.
Thank you.
Okay, we are back with another workshop with API 3, Ben and Jacob today, but we are not done yet. So yes, be patient. Thank you so much for coming again to do a workshop in person. This is amazing. We had a workshop for ETH Barcelona actually live on YouTube, and this is just the beginning of us doing collaboration and providing developers tools for them to build and integrate with different technologies. But yes, without further ado, thank you, Ben, for coming, and Jacob, the stage is yours.
Thank you very much. I mean, yeah, thanks for putting this all together. Albie, it's been great. Yeah, we're going to just talk through today two parts. The first part will be an introduction to API 3 and a little bit about Oracle. And then Jacob's going to talk you through a bit about Oracle extractable value, which we'll touch on later, and basically how you can apply that to protocol design within lending. Just to start off with, a little bit about API 3. The core team, the founding team as such, have been involved with Oracle since 2018. We wrote a white paper in 2020. Fast forward to today, we're about 35 to 40 people globally distributed, like most places. We operate as a DAO, and what we focused in on is building first-party oracles. And just a quick intro to myself, I lead our ecosystem sub-team. Jacob is our research engineer, and we've both been with API for about 2.5 years, I'd say. So yeah, I mean, the white paper, the API 3 focuses thesis on was really focusing on solving the API connectivity problem. As many of you may be familiar with or aware of, many Web 2 applications have become more sophisticated for using APIs. It's allowed people to build more complex applications without the heavy technical lifting. But APIs at the moment are not directly interactable with smart contracts. And yeah, the thesis, the white paper outlined, and what the focus of first-party oracles is making it very easy to bring that data on chain. There's a lot of blockers, there's a lot of problems, not problems, but there's a lot of road blockers that stop this data easily being served to protocols. And yeah, we've kind of simplified that by building a very simple, lightweight first-party oracle, which we called Airnode. It's a very easy way to let API providers operate an Oracle node. It's very easy to deploy, it takes about 30 minutes. Once it's deployed, it's maintenance free. It's set and forget philosophy. It's effectively a AWS or Azure Lambda function. And there's two key parts. Airnode itself is deployed to the API architecture. So the cloud's infrastructure of that API provider effectively is wrapped by Airnode, turning it into a smart contract address. There's then, well, you can use a different type of Oracle protocol depending on the use case, but you have request a contract, waiting for requests or serving requests to Airnode, and then whichever protocol contract it is, it will wake up Airnode and serve that data on chain. Think about price feeds; they need to be updated regularly, so you don't use a different protocol. If it's weather data, perhaps you have a different type of protocol which is more effective for that use case. And yeah, something that we believe in is that the infrastructure of smart contracts, as the space evolves, long-term should be decentralized. The DAO provides that transparent mechanism for people to come in and understand the decisions we made, well, not only just understand, but also contribute to the decisions that we want to make. And we see that it's important to involve the API provider in this broader ecosystem. Long-term means the people that are serving data, they're delivering services to smart contracts. And yeah, that involvement and participation is quite important for us over the long term. Of course, we also enable people to contribute. It's a very flexible environment for developers to come pitch ideas. Jacob introduced OAB 9 months ago and shifted maybe the direction overall, but and for the better, of course. So, and then just diving quickly into oracles and the DeFi sector. So yeah, so there's different types of oracles. People may not realize different models or mechanisms that price is updated with. The most commonly known type of oracle is a push oracle. You have the price effectively kept updated on chain according to different deviation thresholds, heartbeats, and
yeah, you can have, let's say, a 1% deviation threshold every time price moves 1%. That automatically triggers a price update. If you have 0.2%, let's say, you'll have a very granular feed. Of course, this is all underpinned by gas overheads. But what it enables DeFi protocols to do is just have a consistently or more or less consistently updated price for them to read. If you're in lending protocols, you can execute against that price. Trading protocols might want to use a different mechanism because it's a bit more effective for their UX. But the challenges with push oracles can be that if you have a large aggregated set of nodes, very tightly deviated, you're going to have a lot of gas overheads associated with that feed. And the question is kind of, how does this evolve over the long period, over the long term? At the moment, do the chains start to subsidize this? Do the dApps pay for this? Of course, the oracles pay for this, which is maybe what we're seeing at the moment. And yeah, the challenge is like, how do you create that sustainable oracle service for people without maybe subsidizing it heavily over the long term? And then you have toll oracles, which have been introduced probably over the last year or two, where basically, if you're when you are requesting a price, perhaps within a trade, part of that transaction being sent through to the dApp pulls that data as the user comes in and requests it. If you're opening for 20x long, you need to have that accurate price data when you're executing that position. And then what it allows you to do is have like a reactive feed search. But again, it comes to different, the challenges associated to this with the way that protocols are currently designed, don't necessarily directly read Oracle, and that introduces different complexities. And yeah, the user ends up paying for the gas fee, essentially, at high level. We'll talk through the market, but what's your thought? Okay, we'll do that. So I guess just quickly demoing the market that API built. So this is zkSync through a testnet. We still be on mainnet. I'm just waiting for the RPC for it to be available or set up. But yeah, I mean, a user comes through into the market. Here we have Apple USD as an equity price feed. Users at the moment have two options to utilize. There's a self-funded model where you can come in, you can fund gas for the Oracle updates. It's a very permissionless, flexible way to use an Oracle, but it's effectively a single source. Or you can have an aggregated feed, which we operate as a managed service. So we mitigate all of the overheads associated with operating the feeds, pick up the gas transaction overheads. And at the minute, we're just pricing this as, the fee that you pay is just the costs of operating the gas required for the updates. It's very simple to use. You can see we have about 170 feeds, maybe a little bit more. Yeah, we'll soon have this basically fully available on mainnet. I'm going to pass it over to Jacob to talk through the interest of it, basically.
All right. Hello, everyone.
Just don't click on the arrow, maybe.
Okay. All right. Sorry about that. Okay. So OEV. So let's get started with what is MEV. MEV is a hidden fee imposed on blockchain users by more strategic third parties. So this usually comes from maybe reordering your transaction maybe censoring a transaction, maybe adding a transaction right behind your transaction. So example of this is sandwiching. You've probably heard of if you're familiar with DeFi. So if the original transaction is the user, so maybe they're trying to buy 50 ETH worth of Pepe, and a searcher, which is what you call a person running an MEV bot, will see this in the mempool and insert directly before and after your transaction their own transactions within the same block. So they might buy 100 ETH of Pepe for 200K USDC. This will push up the price for the user, and then immediately after they can sell that 100 ETH for some profit. So maybe 220K USDC, and then walk away with 20K of free profit, essentially. So introducing MEV Boost, which is the newest version of MEV options on Ethereum mainnet. So what MEV Boost is it's an off-chain sealed bid option implemented by Flashbots and the EF. And it hosts an option for the right for the searcher to perform something like that. So maybe if they're making, and the profits go to the validator who was proposing that block. So if the searcher is making 20K USDC, he might bid, okay, if the validator chooses to include me in this block, I'll give you 10K of the profit. Or it's more like probably like 19K of the profit, because it's a very competitive auction. So the bids get driven up very high and the searchers have very small margins. So this has resulted in a lot of money going to Ethereum validators. So since the merge, there's been $312 million worth paid to validators for MEV. So this is obviously a big deal. So what is OEV? OEV is the subset of MEV related to Oracle transactions strictly. So MEV that comes before or after an Oracle transaction directly in that block, or from the lack of an Oracle transaction, updating a data feed and causing a stale price on chain. So liquidations are probably the main one. And this type of MEV is actually unique in a sense because it's encoded into the protocol and it's necessary for lending protocols, where other stuff like sandwiches, was not encoded into AMMs or Uniswap. So Oracle latency arbitrage is more similar to sandwiching or backrunning on an AMM. It's just a side effect of a DApp design that is not completely aware of MEV or hasn't solved for it. And Oracle attacks are technically another form of OEV, but this is malicious, and the talk won't really be about that. Oracles kind of are designed from the ground up to avoid those type of things. So, what is MEV share? Has anyone heard of MEV share at all? Raise your hand. No? Okay. So yeah, at least if you get something from this talk, at least you'll get this, and it'll probably save you some money if you're trading on Ethereum. So MEV share was implemented by Flashbots, and there's another similar product called MEV Blocker, which was built by the Gnosis team and CowSwap together. So these are known as order flow options, and it's kind of the new iteration, the newest hot MEV topic after MEV Boost. So we mentioned before, like there's all this money going to Ethereum validators, and it's coming right out of user pockets. So order flow options like MEV share are designed to give this value back to the user. So you have this example here. A user's trading 10 ETH for $73 of WUF work. So obviously this user has made some sort of error when they're interacting with the Uniswap front end, like they've routed it through the wrong pool or something like that. So, but they've chosen to send it to MEV share, which is just an RPC you can add in MetaMask. So what MEV share does is it takes this transaction and it shares it with a network of searchers, who again are the MEV bot operators. And then these searchers participate in an auction for the right to backrun this transaction. So very similar to MEV Boost, where searchers are bidding to validators, but here MEV share makes the user the auctioneer, who's getting all the value back to them. So the searcher backruns this and pays 4.3 ETH. So clearly the searcher is able to make more than 4.3 ETH by being the one to backrun this transaction and arbitrage some Uniswap pools back into where they should be. And the user gets paid for this ETH back. They don't get paid the full amount because some still goes to validators to make it sort of incentive compatible, so validators don't want to censor it. But yeah, so simply by adding a different RPC, this user's now gotten 4 ETH that they otherwise wouldn't have. So yeah, that's pretty cool. So if you're making trades on Ethereum, definitely switch to this RPC. And so now we move on to, that was MEV, so now we'll kind of move back to OEV. So how do liquidations in DeFi work? So when there's over-collateralized lending, you must deposit more collateral than you borrow, and it's based on some ratio. So the rules of the protocol might be, if you deposit $100 worth of collateral, you're allowed to borrow $60 worth from the protocol. So this is, think like Aave, but the same thing can happen with derivatives like synthetics or GMX. You're putting in collateral and you're borrowing something on top of this to get leverage in that case. So there's a health ratio, which basically says like how healthy is your loan? How close are you to being liquidated? So if you're allowed to borrow $60 off of the $100 of your collateral, if you borrow 59, then that means you're very close to being liquidated because you're sort of $1 away from the maximum amount you can borrow. So say if your collateral, the $100 worth was in ETH, and ETH price goes down to $90, now all of a sudden you don't have enough collateral based on the rules of the protocol. You must have $60 for $100, 60%, and now if your ETH is worth $90, your loan can be liquidated. And that's how the lending protocols operate and stay safe and manage to not lose the lender's funds. So how exactly does this liquidation happen? Liquidations have to be done decentralized in order to be safe. So instead of Aave, instead of Stanny being the person running a bot and saying, oh, I need to liquidate this person, like what happens if that liquidator was asleep or gets hit by a bus or anything? You need a decentralized market. So the protocol will implement a discount factor. So they'll say, whenever a loan is below its collateral ratio and it can be liquidated, then anyone can do this liquidation and you'll receive the discount factor, which is usually like 5 to 10% of the collateral. So if it's a $100 loan, the liquidator comes in, they can make $5 off of that. And that's how protocols basically guarantee that liquidations always occur, because someone's always incentivized to do it. Obviously, if the profit is more than gas costs, of course. So OEV share. So think Mev share, but for oracles instead of for users. So oracles can't effectively use Mev share because in the example where we had a user sending a transaction to Mev share, the transaction they're sending is creating MEV for themselves. So all Mev share has to do is give them the value back. But with oracles, when they're sending a transaction, the MEV is not being created for the oracle itself. If they're sending a transaction, some third party might be getting liquidated. So maybe like Bob is getting liquidated. And when the oracle's sending their transaction, they have no idea about Bob's loan. They don't know, maybe some other guy's going to get liquidated from this as well. The oracle has no practical way of really knowing this before they send the transaction. So that's basically the reason why MedShare is just not, it just can't be used by oracles, really. So in comes OEV share, and this allows the searchers to request oracle updates from the oracle itself. So a searcher sees that, oh, Jim can be liquidated. They go to the oracle and they say, okay, please give me a data feed update to update this data feed, and I'm going to liquidate Jim with it. So the oracle then takes this and signs the data feed update, which they're just signing a price that then can be used to update the DApps data feed. And they also sign the wallet address of Jim, like whoever the searcher has said that they want to liquidate. So then now the searcher has this, and he's only able to use this data feed update to liquidate Jim. So now that you've done that, the protocol can send the bid directly to Jim because he knows this data feed update can only be used to liquidate him. it knows exactly where to send the value. So how do liquidations work via OEV share? That was basically what I explained in the last slide. But so searchers determine the prices that will cause liquidations for borrowers. They tell Oracle, hey, if the price goes below this certain point, please give me an Oracle update. And they base their bids off of how much profit they can make. So if they can make, like, if the discount factor is 5% on $1,000, they're making $50. They might say, okay, I'll give back this person $40, and that'll be their bid, because they still walk away with 10. And if the auction is competitive, they'll want to send high bids to make sure they get it. And again, it's a sealed bid auction, which just means that people making bids can't see other people's bids. And what this basically does is it forces people to bid really high, because if you can see other people's bids, then you might just start low. If you can make $50 off this, you might just start at 1, and maybe someone else bids 2, and then you see, oh, okay, all I have to do is bid 3 to win. But if you're unaware of anyone else's bids, then you're just going to basically bid the maximum amount that you're willing to pay right off the bat. So the opportunity. In the last year, Aave paid out $14 million in these discount factors as incentive to liquidators. And much of this would have been overpaid for the service. So, like, the discount factors are fixed. So if there's $1 million loan, the incentive would be $50K to perform this liquidation. And that's much greater than the gas cost. The gas cost at most on Ethereum would maybe be $1,000 to do a liquidation like this. So someone outside the protocol is walking away with $49,000 of someone's collateral. And these things add up to, $14 million. So it's a big problem. And if you fix this, there's a really cool flywheel effect that can happen. So if users know that, hey, if I'm borrowing from this, I'll get liquidated and I could potentially lose 5%, that's pretty scary. So if you implement something like this where you can give a lot of that value back to the user, maybe you say, okay, if you get liquidated, maybe you'll just lose 1% or 0.5%. All the borrowers are going to borrow from this protocol because it mitigates their potential loss. And if you start attracting all the borrowers, then that raises the lending APY in that protocol as well. So it's this flywheel effect. If you get more borrowers, you attract more lenders, you get more borrowers, and it just leads to getting a lot of TVL for your protocol. So Euler Finance, has anyone heard of them? They got to 300 mil TVL at their peak on Ethereum mainnet, and their main value prop was this, what I just explained. They implemented an auction for their liquidations and gave the proceeds back to the borrowers. So it was an Aave fork that did this liquidation auction, and they were able to be very successful. So there's clearly demand for this service. So how did the Euler liquidation mechanism work? So it's a Dutch auction, and the discount factor is just the difference between the liquidation price and the Oracle price. So if someone can be liquidated when the price of Ethereum goes below $1,000, maybe they have 1 ETH, and the price of Ethereum, and they get liquidated below $1,000. So say the price drops down to 990. So the discount factor is just the difference between the current price and when they would have been liquidated. So if you get liquidated at a price of 990, then the searcher only gets $10 as their discount factor. So it's just that difference. And that's able to mitigate most of the potential loss for users. But there are some problems. So this is a screenshot of a Euler liquidation transaction. And you can see there's still about 0.1 ETH going to the Flashbots builder. So what this transfer is it's a bid to MEV Boost that we were talking about earlier. So this is going directly to the validators, 0.1 ETH. So this shows that whatever Euler did, it was not a full solution. They're still leaking a decent amount of value to validators that could have been going to users. So why is this happening? Well, it kind of has to do with oracles not updating every time there's a price change. So like Ben was explaining earlier, oracles only update when the off-chain price crosses a deviation from the on-chain price. So let's go back to the example of the user being liquidated when ETH goes below $1,000. If the oracle price on-chain is showing $1,001, he's safe, he cannot be liquidated. But then let's say the off-chain price drops to 995. If the deviation threshold might not have told the oracle that they need to update this price yet, because the difference is not, it hasn't crossed that deviation threshold. So the off-chain price is 995, the on-chain price is 1,001, and this user can be liquidated when the price goes below $1,000. So maybe in this Euler Dutch auction scenario, the searcher was willing to liquidate him at $995, but he can't because the oracle hasn't updated on chain yet. So by the time the oracle updates on chain, maybe the price is down to 990. So the searcher was willing to do it for $5, but they couldn't because of the oracle design, and they end up getting $10. And then what happens with this excess value is you go from the Dutch auction implemented by Euler, and then there's now a second auction on top, because once you've got the oracle price, everyone in the world has that price, every searcher that you're competing with. So now you have to participate in a second auction to pay the validators for the right to get your transaction included first over everyone else that has this oracle update. And that's why there's this 0.1 ETH going to MEV boost. So how can we fix this problem? How can we get the maximum amount of value back to the user? So OEV share unifies these liquidations into a single auction, because you don't have to wait for the deviation threshold to be crossed. Instead of that, the searcher can say, hey, I was willing to liquidate this person at 995. So he tells the oracle, if the price ever goes to 995, please give it to me, and then I will perform that liquidation. So they didn't have to wait for the on-chain price update and it go down to 990. And when you win an auction in OEV share, whoever wins that auction is the only person that has access to that data feed update. So whereas before with the Euler thing, when the on-chain price updates, everyone has access to this. So with OEV share, the winning searcher is the only one that has access to this. And this allows them just to send the base gas price and get included in the next block. So they don't have to participate in that second auction for block rates. So instead of having to pay that 0.1 ETH to flash bots, that value can then go to the user when a lending protocol or a derivatives protocol uses OEV share for liquidations. So how exactly does this work? The OEV protocol uses proxy contracts to get a fair distribution of OEV. So this is a contract that the protocol reads from. And every protocol has application-specific contracts. So the way oracles work today is there's one ETHUSD contract. All the dApps read from this. It's the one source of truth. How it works with OEV is there still is this one ETHUSD contract, but each dApp also has their own specific data feed contract. So there would be an Aave ETHUSD, a Maker ETHUSD, a Comp ETHUSD contract, and so on. And what these application-specific contracts do is they just check, okay, is the price in my ETHUSD feed more recent than the price in the generalized OEV feed? So the original ETHUSD feed, is just still being updated by the oracle. But the application-specific feeds are updated by OEV share. So because the application-specific feed just wants the most recent price, that means if there's no updates from OEV share, it just reads from the normal ETHUSD feed, like any other application would presently. But if someone comes in and updates it with OEV share, it reads from that. So it's just a way of allowing there to be application-specific updates. And why do you need application-specific updates? This goes back to what we were explaining earlier of why oracles can't use MEV share. So if you force them to make an application specific update, you know exactly where the value is going. So instead of just updating the data feed saying we're going to update ETHUSD, you don't know if, again, Jim or Bob is being liquidated on Aave or Maker or Compound. But here you force the MEV searcher to say, okay, I'm performing this liquidation on Compound. And the data feed update is signed in a way that it can be only used on that application. So you know where to send the OEV, you just send it to Compound. And that is what allows for fair distribution of OEV, and it's basically the main reason that makes this better for oracles to use than something general like MEV share. So this is just if you like code, then more than me kind of just talking about it, then you can look at this, and this is just the function you read to get the price from the application-specific contract. So you can see it's reading the normal data feed value, the generalized ETHUSD value, and then here it's reading the one from its application-specific OEV feed. And all it's going to do is return the most recent one. So how can we actually build this liquidation mechanism that is better than Euler, technically? So in that example before, the data feeds were application specific. But to build a protocol that gives the bids directly back to the liquidated user, the proxy contracts actually need to be user or borrow specific. So the protocol would have to deploy a new proxy contract for every user that takes out a new position, a new loan. And for each new position they're taking out a loan on. So what you'd want to do is when someone's opening a position, you check if they have an existing proxy contract. If they don't, you deploy it for them through the proxy factory. And the beneficiary, so I'll just quickly go to the next slide. So this is what it looks like when you're deploying these application-specific OEV contracts. You just have, this is the general API 3 contract that you read normal data feeds from. The DAPI name hash is just specifying like what asset this is, so ETHUSD from the API 3 contract. And then this is the part you really need to worry about, the OEV beneficiary, which is who gets sent the funds when there's an OEV update. So when you're doing this, when you're deploying the proxy contract for each user, you're setting the beneficiary to that borrowed user. And then this is what forces searchers to, if they want to liquidate this person through OEV, they have to pass in the address of the borrower. And then to liquidate that user with an OEV update, it has to go through the borrower's proxy. Okay, so we went over that users want this product. You can clearly see the demand with Euler. And this is necessary to help compete with centralized finance because users can't just be losing 5% if they get liquidated. That's not how it works on Binance. That's not how it works on FTX. It's definitely not how it works in traditional finance. So yeah, let's get some builders building this.
Thank you very much, Jacob.
So any questions, comments?
Definitely needed.
Thank you. And yeah, if you're not a builder building that, then just remember to use MEV share to save yourself some money if you're doing an AMM swap. Cool.
Well, we don't have any questions from the YouTube, so yes, thank you for your presentation.
Thank you.
And yes, we'll be for 2 minutes off until we have our next speaker on stage. Well, we are back with another workshop, and the last workshop for today with Dustin, our DevRel engineer at zkSync. For all of you who want to learn about building on zkSync or building on Era, this is the right workshop to be in. And for all of the future listeners and the current ones, listen up closely because you will need all the details that Dustin will share with us. Dustin, say this first. Thank you.
Awesome. Thank you very much. Hello, everyone. Thank you for coming out. How's everyone enjoying Paris?
It's great.
I need a little louder than that. Everyone enjoying Paris? Yeah. The audience here is absolutely deafening. I'm super excited to be here. It is a fantastic to be here to talk to you about Era and building on Era. This is going to be a presentation where we're going to build out a little application and kind of walk you through the steps of how to do so. But first, let me give a little introduction to myself. My name is Dustin Brickwood. I am a developer relations engineer here at zkSync Meta Labs. You can see my GitHub handle there if you want to follow around all the open source contributions. And I just rejoined the Twitter sphere, so if you could give me a follow at DutterButter92, you can stay up to date with all the latest and greatest on zkSync Era. All right, a little bit of an agenda for you. We're going to go through a bit of a development landscape, give you the lay of the land and how to go ahead and build these applications. We're going to outline some learning outcomes that I hope this raging audience leaves with today, especially those online and watching from home. We're going to jump into some code and actually build out a little application. We're going to review some key takeaways that I hope you guys can leave with, and then a bit of a call to action that I expect everyone to do.
Okay, we're good.
Awesome. So how to build on zkSync Era. This is very high level and just a bit of an overview of the process. We're going to write our contracts in Solidity or Viper. So this is just like you would in Ethereum, and that's the goal of what we're trying to achieve, make it feel and just like Ethereum. So you can either migrate your contracts over or you write them directly in languages that are very familiar. We're going to compile our contracts with the zkSync Era compilers, zkSolC, which is for Solidity, and zkViper for Viper. These are specialized compilers that output the bytecode that is compatible with our zk EVM. We're going to deploy some scripts using hardhat deploy, or in this particular workshop, the zkSync deploy. And you can use one of our many SDKs for scripting or front-end integration, which today we're going to make use of zkSync Web 3, which is the JavaScript SDK. So developer tooling, we're going to talk about the zkSync CLI, something that I use literally every day, and it's awesome. We're going to do an overview of some of the SDKs that we offer. We're going to talk about the hardhat plugins that we also support, and we're going to talk about a little bit of the third-party tools that the team certainly enjoys. So zkSync CLI, this thing is awesome. I use it every single day. It's a command line tool to simplify the process of developing applications on zkSync Era. So you can deposit, withdraw, and scaffold new hardhat projects. It is the easiest way to deploy a contract quickly to zkSync Era. If you haven't deployed anything yet to zkSync Era, I highly recommend installing this CLI. Globally, just zkSync CLI at latest, and you can deploy a contract in under 60 seconds and just get a feel of what zkSync offers. It's as simple as running the create subcommand, and you have a brand new project. And it comes out of the box with a hardhat configuration and a greeter contract and a deployment script. So all that overhead is taken out of the way, and it's completely convenient. So hardhat plugins. So we have 6 hardhat plugins that could be installed independently, or if you want to have all of them available to you, you can use the hardhat zkSync toolbox, which combines each of them. We already talked about the hardhat zkSync SolC and hardhat zkSync Viper. These are for compiling contracts for zkSync Era. We have the hardhat zkSync upgradable plugin. So this allows you to create, deploy, and update your contracts, very similar to OpenZeppelin's upgrade plugin. For contract verification, hardhat zkSync Verify. So you can verify those contracts on the Explorer. We have hardhat zkSync Chai Matchers, because I hope everyone here is writing tests for their contracts. You better be. And the Chai Matchers provide some helpers to make that even a bit more convenient for you. And then for deployment convenience, we have hardhat zkSync Deploy. And And again, it just provides a little bit more convenience in that development workflow. Commuting plugins are also supported. So if you're very familiar and you like to use Hard Hat Deploy, you certainly can, or TypeChain, or any of these other community plugins. They'll certainly work with zkSync Era. And here you kind of have a pretty generic Hard Hat configuration that probably feels very familiar to anyone who's done Ethereum development before. We have SDKs for some of the most popular languages and more to come. So JavaScript SDK is zkSync Web 3, which we'll use today, and it's based on Ethers.js. You can see a bit of a snippet right here. It's going to look very familiar to you if you've used Ethers.js. The same classes are going to work right out of the box. So you can see provider and wallet class. It looks very familiar because it is. It's just basically an extension of. We have a Go SDK that's based on Go Ethereum, a Python SDK based on Web3 Pi, a Java SDK, and a Swift SDK that is going to be shipping soon. So definitely, if you follow me on Twitter, you'll get the latest updates, and I'll let you know.
Woo!
I like that. It's audience. And of course, I forgot to mention, if you want to dive into our documentation and any of these SDKs, what you're going to find is a lot of examples and a lot of explanation. So definitely go check it out. So third-party tooling. Because we are EVM compatible, there's a lot of tooling that comes right out of the box that's easy to use. Atlas, which is very similar to Remix, which is a browser-based IDE that comes with an AI that generates smart contracts right near your side. So it's if you're familiar with GitHub Copilot, it operates the same way. It's pretty cool. ThirdWeb, who actually presented today and showcase their dashboards and their easy contract templates. And ZetaBlock, so very similar to June Analytics. If you're a data scientist or you like data altogether, you can build some dashboards. There's certainly a lot out there for zkSync Era that you can review. And yeah, all this is going to work right out of the box because, again, we're EVM compatible. We just released an alpha version of Foundry zkSync. So if you prefer that tooling, you can compile and deploy and interact contracts with zkSync Era using this, which is awesome. All right, so demo requirements. We're going to go over some learning outcomes. If you recall, we'll kind of go over some of the build requirements. I will prelude that in terms of these workshops, I like to dress up the build requirements a little bit to try to give the audience a little bit more entertainment. So I'm also a big nerd. Well, based on my height, you probably think I'm a small nerd, but nonetheless, it's just for entertainment purposes, and it gives us something to look forward to during the code workshop. So learning outcomes. What are you going to leave here with? You're going to learn how to write, compile, and deploy smart contracts on zkSync Era. You're going to learn about conditional paymasters and some of the validations that you can do. You're going to learn to build a paymaster that covers your gas fees only if they possess a specific NFT. And you're going to learn how to interact with these deploy contracts with a front-end app. So those are learning outcomes you're going to leave here with. So let's get started. What we do, I like that. Stark Industries needs to assist the Avengers in covering gas to travel the zk Era universe. Can you help us in our mission of building a gated paymaster? Enabling the Avengers to focus on their mission, not on the cost of transaction fees, is our highest priority. And that was a message directly from Pepper Potts, the CEO of Stark Industries. They want our help, and we're going to help them. And although this is fictional and fun, it does provide a little bit of a value because we want product teams and developers to focus on the value that they bring to their users, not on the transaction fees. And that's exactly what Paymasters and Account Abstraction provides. So what are we going to build? The idea is simple. The ARC Reactor, an ERC 721 gated Paymaster to empower the Avengers. Only the Avengers carrying an NFT stone, an NFT, are eligible for Stark Industries gas coverage. So we're going to get our hands dirty and actually write some of these contracts and build a bit of a front end that interacts with these. I am going to be using a bit of a template that I prepared for today. And based on some of the internet qualities, I've actually went ahead and uploaded some of the metadata for these NFTs on IPFS already so that we don't have any troubles here. It's going to be a part of a starter template that we use. So we're going to shift over here to some code. You guys can see my screen okay? Awesome. So here we have a project structure. It's using kind of your own workspaces for easy dependency management between these two projects, as well as some simplified scripting. We got a question. I love it.
Yeah. Do you think we could go back one slide so I can clone the repo and follow along?
Is
that possible?
I would say it's probably not possible for this particular, just because I'm going to be going pretty quick using code snippets. But there will be all this available open source that I'll be happy to share, and a tutorial so you can go through this at your own pace, which is awesome.
You mind zooming in just a little bit to see
Yeah,
the
absolutely.
font a little bit?
Yeah, the audience.
There you go.
Yeah, I like it. Awesome. So see my screen even better?
Yes.
Perfect. So we have two directories here. Front end, which is going to house all our components and styling and our kind of React Next.js project structure. And then we have zkSync, which is where our contracts and deployment scripts are going to live in our hard hat configuration. We're going to start here because we need to write and deploy these smart contracts before we can actually interact with them. So this hard hat configuration, again, if you recall, this is going to look very familiar. We are utilizing our hard hat zkSync sol.c to compile these contracts because we are writing them in Solidity. We're going to make use of the hard hat zkSync deploy, which will provide some convenience for us. And we're actually also going to use the zkSync verify because we're going to, in our deployment scripts, we're going to actually verify these contracts on the Era testnet block explorer. As of 0.4.0, you can actually, you don't no longer need to specify a version number. You can just say latest, and it's going to bring in the most stable compiler, which is awesome. So in our contracts directory here, you can see 3 contracts: ERC 721 contract, which is going to be our Infinity Stones, our ERC 721 gated paymaster contract, which is going to be our Arc reactor, and our greeter.sol contract that again comes out of the box with that zkSync CLI tool, and that's going to be kind of how we're going to demonstrate these interactions. You also notice there's a metadata file here. Like I mentioned, this has already been kind of uploaded to IPFS just for convenience, just so that there's transparency there. All right. So we have this ERC 721 Sol contract here. You can see that we're making use of the Open Zeppelin standard libraries, and specifically the ERC 721 URI storage, which is an extension of ERC 721 so that we can link this kind of unique URI to these Infinity Stones. We have the ownable library just for some access control, and a strings.sol just for some utility helpers. So here we have our 6 Infinity Stones, which of course there's only 6, so we have them neatly outlined there. Here we're going to actually implement the mint function. Again, I'm going to make use of code snippets just for the purpose of this demo, but here we have our list of requirements. We've got to make sure that only the owner of the contract can mint these stones, which we're making use of the only owner modifier here. The stone name must be one of the 6 stones, so one of these 6 stones. The stone name must not have been minted before because, of course, there's only going to be 6 Infinity Stones. The stone name can't be empty, and the recipient must be a valid non-zero address. So these are just kind of checks that we have to have in place. So I'm just going to go ahead and use my fancy little code snippet here to make things a little bit quicker for us. Here we're doing those validation checks to make sure that the stone name is not empty, we have a non-zero address and it's valid, and that the stone name hasn't been minted before. So we've we're kind of looping over each of those stones names, using a kickback 256 hash to compare those to ensure that the stone name is one of the 6 of our listed Infinity Stones, and then we're actually going to mint those stone names based on the recipient address that we're going to pass in, which is great. And we've kind of accomplished the requirements that we've kind of outlined here. And I'll just go ahead and just for readability move that along. And I apologize for the formatting here, but we're using GitHub's code spaces, so none of the extensions are really helping me out here. But we have our Infinity Stone NFT contract ready to make use of them to mint these Infinity Stones to a recipient address. So we're going to move over to our Arc reactor so we can build that out and make sure those validations are in check, that we're only going to pay for the gas fees for users or Avengers if they have an Infinity Stone. So here, we make use of some of our own libraries, specifically the iMaster interface and our iPaymaster flow. These are interfaces used for your convenience, as well as to provide standardization with our paymasters. So here we have our contract for our ERC 721 gated paymaster, and where we have this validate and pay for the paymaster transaction. This is where all the good stuff is going to live, and we're going to implement. This is where we're going to put in some certain conditions, and it doesn't necessarily have to be the condition in which we're implementing today. It could be whatever condition that you particularly want to deploy for such things as, if you want to do an allow list where you only certain addresses qualify to get gas fees paid for, you can do an allow list type of contract. Or you can keep it open and have a gasless paymaster that facilitates for all transactions. So here we have, again, some requirements to be implemented. So only the bootloader can validate and pay for paymaster transactions. The standard paymaster input must be at least 4 bytes long. We must use a valid paymaster input selector. So for our implementation, there are 2 particular flows, a general and an approval based. For this particular workshop, we're going to make use of a general, but an approval based is when you're making use of ERC20 tokens, in which you have to set an allowance in a particular token that the paymaster will have to exchange for ETH and then ultimately pay for those gas fees. The user address from this transaction must own a required NFT to use the paymaster. And then we need to calculate some required ETH to actually execute that transaction and pass it along to the bootloader. So we'll do some nice magic here. And here we do our requirement check to make sure that that input length is at least 4 bytes long. We specify our flow as general, and we're doing a requirement check to ensure that the NFT balance of the user address is greater than 0. If not, we're going to let them know, like, hey, you have to pay your own gas. We calculate the required ETH in order to succeed in this transaction, and we pass that along to the bootloader to actually execute the transaction and ultimately pay for the gas fees. So once again, we have successfully accomplished our requirements, and we will save that. And we will actually, I'll go over the greeter contract just so that there's some awareness. So this comes again right out of the box. So you have your basic functions for greet, which was going to return an arbitrary message, as well as set greet, so that we can change that message. So now that we have our contracts built, our Arc reactor, I should say, we're going to compile those contracts. It take a little bit longer than usual, just because we're using GitHub code spaces, but nonetheless, it's going to compile those contracts. It's making use of the zkSync version 1.3.13, and we have successfully compiled our contracts. Now we need to deploy them. So we have a series of deployment scripts here. For instance, like deploy greeter, and here we kind of specify, what that first message is going to look like. Can I get a suggestion from the audience? What message should we use with greeter first and foremost?
Dustin, you're the best.
Dustin, you're the best. I like that. I like that. Dustin, you are the best. I'm just gonna say Dustin the best, just to keep it short and friendly. Nonetheless, I love the suggestion. Here we have the other deployment scripts, and we've kind of set this up just so that it's going to deploy each of those contracts, and we're going to first and foremost pass it an address so we can send the NFT that we mint, so we can make use of this in the front end. So I'm just going to go like this. First, I'm going to grab an address, just so that's easy. Awesome. It's asking me for that address. Let's allow that. So here we're going to mint this, the first NFT or Infinity Stone to this address. And it's going to go through and deploy each of those contracts for us once the internet participates. So here I was minted the Power Stone. That makes sense for me. And it mentions that we have a balance of 1 there. So that's good. And here you can see that we got our NFT contract address, which is awesome. We've verified this on the testnet, so let's go ahead and check that out again here. Testnet. Awesome. So here you can see the contract, so it's successfully verified, which makes it very easy to do so programmatically. Awesome. So it looks like it all successfully deployed. And so we're done with the smart contract perspective. And now we're going to head over to that front end project directory and build out our kind of application to interact with these contracts. Awesome. So here we have our project structure is pretty simplified. We have a components directory, which is going to house all those React components. We have our hooks and our types and our context directory to help out a little bit as well. And we have this kind of main parent component under page.tsx, which is going to be kind of like our starting point. If you can check it out here first and foremost, just to see what we're starting with. So I'm going to open this browser here. It'll take a second. It's working hard behind the scenes. I'll come back to it. Awesome. So in our components, we have our checkout component, our greeter message, input, modal, text, and wallet button. We're not going to play with all of these, but they're going to come out of the box. And if you're following along with the tutorial, you can make use of those as you see fit. It looks like we are awesome. So this is with the starting point of the template. It's very basic. We have this connect wallet button that we're going to implement some logic for. And of course, you can see what's missing here is we have no input box to actually engage with that greeter contract, but we'll get there and we'll implement that. So we'll start with our wallet button so that we can kind of connect to our MetaMask account and then also initialize the NFT contract and the paymaster or the greeter contract. So here, again, we have our list of requirements. We have to ensure we're connected to the correct network. We're going to connect to that user's MetaMask account. We're going to set the provider and signer for later usage in some local state. And then we're going to instantiate those contracts. Again, I have some fancy code snippets just to run this along, and we're going to make use of it. So here, again, we're going to check the network, make sure it's connected to zkSync era testnet. We're going to connect to a provider and prompt MetaMask to connect to our account. And we're going to call this a init contract function, which is going to instantiate our greeter and NFT contract. So we'll go up here. Of course, we have our requirements again. You're going to get very tired of me saying that word, but nonetheless, they are outlined for us for simplicity. We're going to create a new contract instance for the greeter contract, as well as our Infinity Stone NFT contract. We're going to call that greet function from our contract to get that initial Dustin is the best message so we can render that on the page. And then we're going to do some extra checks to check the NFT balance of the signer's address just so that we can understand how that operates in our front end. And we're going to set some state variables just so that we can pass those along to the other components. Wow, I code fast. So here, again, exactly what we were doing. We're going to instantiate those contracts. We're going to fetch that initial greet message, and we're going to set some stuff into our local storage. Here, again, like I mentioned, for convenience, I've already uploaded the metadata for those NFT contracts to IPFS. So we're actually going to go fetch that data from IPFS just so that we have that available to us. So we're going to save that. Of course, these things are always in the way. Great. So we're going to connect to our wallet here. It's going to ask me to connect. Let me say yes. Boom, we're connected. That's awesome. But we still don't have our input box or our greeter message. So we have to go ahead and implement those. So we'll head down to our parent component, which is this page.tsx file. And here you can see we need to import the greeter component, pass it some props, as well as our input component. So let's go ahead and do that. We're going to import our greeting component, but first we have to, of course, do the top here. Awesome. And we're going to just do the same here for input, so it's easy. Awesome. And we're going to also import our input component. So here we're passing it some of that data that we put in context so we can use and pass to other props like the greeter message and the contract instances. We're going to head over to our page here and give it a reload here. Oh, it's complaining.
You misnamed the import up top.
Did I? Greeter message.
Greet king instead of greeter.
Greeter message, that's right. No. Greeter message, greeter. Greeting, you are correct. This audience has been fantastic today. Boom, there we are. We have our message, and boom, Dustin's the best. Thank you again for that. You did that today. We're not done, but I love the enthusiasm. Great. So now we've done some work here. We still have to, of course, be able to change the greeter message and show that, hey, we're not paying for these transaction fees. So we're going to head over to our input component. And what we do want to render is this nice kind of modal interface that shows the estimated gas that you would pay if, of course, you had to. So we'll start by implementing this gas estimate function here. Just, again, make it nice and easy. Oops. So very familiar to anything that you would do for Ethereum development. We're going to get the gas price. We're going to estimate the gas for that set greeting contract call, and we're going to get the transaction cost by multiplying that gas price by that gas estimate. And we're just going to store that in some local storage so that we can play with that later on. So we have met the requirements, and what we still need to do is render our modal so that when we click change greeter, we can actually see something that pops up. So we'll do that now. We're going to import that modal component and pass it some props so that we can actually make use and see what's going on. But one thing that we haven't implemented yet, of course, is our paymaster hook or our checkout component, which is going to live in this kind of hooks directory here. The internet is killing me, but it will get there, I promise. Oh, internet. Give a load here. It's trying hard, which is, you can appreciate that. Awesome. So we're back online. We have this paymaster hook that we still have to implement. This is where we're going to actually return the paymaster params that we're going to pass to that transaction in order to facilitate that gases transaction. So similarly, we're going to make use of our nifty code snippets if the Wi-Fi helps us. Great. So here we're again specifying the general paymaster flow. We're not going to pass it any kind of payload, and then we're going to set our custom data params that are required in order to facilitate the use of the paymaster, and we're going to return back this payload of what needs to be sent along with that transaction. So we'll head out to our checkout component. This is the last component that we're going to implement, and the last time you'll hear me say the word requirements. So here we're going to update our greeter message. We're going to import our paymaster. Awesome. Defaults. Note that. Great. So here we are going to fetch those paymaster params if the individual has an NFT. And you can see here, we're gonna call that set greeting function call from our your contract instance, and we're gonna pass along that params, and that's what's gonna facilitate that gasless transaction. If they don't have the NFT and they're not an Avenger, we're going to just go ahead and go through with the typical transaction where they have to pay for the gas. So I lied, you're gonna hear the word requirements one more time. We've met our requirements, which is awesome. We're going to serve up our UI again because it closed on us because of internet. We're gonna open this up. Let's get a load for a little bit because it's working hard. We're all working hard out here. It's gonna take a second. So we went on IG. It's gonna get there, I promise. Hey. So again, we have our starting message is Dustin Best. We're gonna change this message. Can I get another suggestion in the audience? Perhaps something a little bit more tailored to Paris or ECC?
Nicholas is the best.
Nicholas is the best. All right, we're gonna go. Nick
French
is the best. We're gonna change this greeting message, and because I was minted an NFT, our checkout here it says, "Congratulations, you own an Infinity Stone NFT. Must mean I am an Avenger." You can see this kind of image of the NFT stone, and here you can see kind of our transaction details. The transaction we're trying to make is that set greeting call. The transaction fee that we would have paid and the gas price, which means the estimated cost would have been this for the user. But because I got that NFT discount on that Power Stone, it's going to be 100% free for me. So I'm just going to initiate that. I'm going to sign this message here, which is going to allow me to pay the gas, not have to pay for the gas. And Nick is the best, which he certainly is. And that is exactly how you can build a little application on zkSync Era and make use of the paymasters that we have to offer. So we'll jump back to the slide deck here.
What does it look like? What does it look like for someone who doesn't have the?
Oh, I love it. Yeah, so we'll do that right now. We'll change my account here to, we'll just go account 1 here. We will connect to this person and we'll just give it, we'll connect. Nick is the best, is the current message right here. Can I get another suggestion? Although I have no Ethan
I'll be
account,
called.
so
I'll be called on socials.
I love the plug. Those on social.
Follow, follow, follow.
And then here you can see, unfortunately, this account does not own an NFT, so you're not an Avenger, and we'll have to actually charge to actually change this greeting message. This will fail because this account I don't think has any. Maybe it does. Nice. Bobby Code's on social. There you go. But of course, I had to pay for that, and it was not gasless for me. Great. And of course, I just want to make sure that, this will be a tutorial in our doc so you can follow along on your own pace, and there'll be the template repo for you to start, as well as a kind of a full code example. But key takeaways. If you've developed on Ethereum, you'll notice that this was felt exactly the same as developing on Ethereum. There was no real difference. We didn't do anything out of the ordinary or anything unusual. We wrote our contracts in Solidity, we deployed them using a hard hat plugin, and we interacted them in our front end exactly as we would. We have strong developer tooling support because we are EVM compatible, but we're always improving. We want to continue to improve that support. Contract development and deployment remain unchanged. Again, when we wrote in Solidity and we deployed accordingly, and nothing really changed there out of my development workflow that I would on Ethereum. Our SD covers multiple languages for convenience, so I use the JavaScript SDK, but of course, if you want to do the same one in Go or in Python, you can do so because we offer that. And Paymaster is a game changer. That was awesome. You could think of so many more use cases where it's not this particularly Avenger NFT gated Paymaster, but it could be something else, something more imaginative. I'll leave it to the builders to come up with these awesome use cases. A little call to action here. We want to hear from you, either in this audience or watching from home. What tooling do you want to see supported? What are specific tutorials that you're awaiting eagerly for us to provide on the doc site or in our community tutorials? We're definitely want to kind of facilitate to what the community wants. So definitely reach out to anyone wearing a zkSync era shirt or on developer discussions. And what other Paymaster examples do you want to see on our Paymaster examples repo that provides out of the box kind of examples of interesting use cases like the gated Paymaster, like the allow list, and things like that. Let us know because we're eagerly waiting to talk to you. Thank you very much. And thank you.
Thank you very much, Dustin, for your presentation. This presentation wraps up all of our BUIDLEra Developer workshops for today, July 18th in Paris. And we thank everyone who attended in person and also who watched live the event for like 6 hours now. We are very happy that we kicked off this type of event, and I feel like we'll bring it in a monthly basis with our amazing DevRel team and with the tools that we are building consistently. Thank you, Dustin, again.
Thank you.
It was an amazing presentation.
Thank
We
you.
needed this energy, which was like the last presentation and the best one. So thank you very much. And yeah, let's see you and you later on YouTube.
Awesome.
Right?
Like and subscribe.
Awesome.